Kau makan ni ada makan kat atas tu. Jadi kau boleh makan kat atas. Tak apa dah. Ataupun kalau tak cukup makan kat education kau minta dia charge lah. Who's chairperson for this meeting? Okay.
Opening sekali kan.
Alright. Aku start.
Okay.
Good morning. Can everybody hear me?
Morning.
Yes.
Good morning. Okay, thank you.
Good morning, Prof.
Thank you very much for joining this workshop. We do really appreciate for the time taken, especially our overseas guests, Professor Azizur Rahman, Professor Ken Grattan, and then we have Professor Najubato from Southampton University, Professor Aru from IIT India, and then we have other people, but some of them will be going online. But the guests that I mentioned just now will have a presentation, but online. But they are here in my office now. So I would like to thank for their effort to take their precious time to come to Kuala Lumpur and to join us for the conference. For the information to everybody, we have invited the Deputy Vice Chancellor of Research and Innovation to have this opening speech, but her mother just passed away last Saturday, so I don't want to trouble her to do the opening remark. And then the other opening remark is from Mike, the funding agency for this project, Datuk Yusof Sulaiman. Unfortunately, he's in Mecca now doing his Hajj. So the timing may be not of convenient for them. My sincere apology, but we have the mic representative Ahmad Razif who will stand in for the CEO of MIC. I'll be standing in for the Deputy Vice Chancellor. Maybe later we can have lunch together with her, Professor Aziz, if she is around. We can have lunch either today or tomorrow. We will invite her to join us for lunch, and then you can meet her. We have a new Deputy Vice Chancellor early of this year being appointed, so we will make sure that you'll be able to see her either today or tomorrow. For this conference, I want to share to all the participants that it's a second international conference which we have been doing from last year. We have the first international last year, and this is our second international conference. This was made possible with the generous support from MIC. MIC is Malaysian industry for Malaysian government industry for high tech. They are the partners with Newton, with British Council to provide this generous funding. We are so grateful, and we have performed very well in this project with so many publications, and we have one patent with Big File, and we have 2 conferences, and then just to share the whole idea about this project is the sharing of knowledge with everybody in Malaysia and also outside Malaysia, what we have done, because that's one of the objectives of the project, sharing of knowledge. So before I take too much time to address this conference, I would like to invite the MIC representative, Encik Ahmad Razif. Hopefully you are here, Encik Ahmad Razif.
Yes, Prof. I'm here.
Thank you for coming. Thank you for for joining us. I think you know this is the second international
Yep.
conference. I hope you'll be very pleased with us. We have used the money very wisely. We have, I think, produced so many publications. I'd like to take this opportunity to thank my partner, Professor Azizo, Professor Ken, Professor Gilberto for the joint publication. Quite a number in very prestigious journal like IEEE Sensor. So I will let you take the mic now to say something, one word or two.
Okay. Thank you, Prof. Assalamualaikum and a very good day to everyone. First and foremost, on behalf of Mike and also British Council, we'd like to express our deepest appreciation to Universiti Malaya and so to Prof for inviting Mike, giving us a platform to give some remarks for the second innovative conference on innovative optical sensor 2022. Like you mentioned earlier, this is the second um, conference that you guys are organizing, which is very, very good. This program is also part of the activity under the Innovative Landslide Detection using Advanced Distributed Optical Sensors project, which is actually sponsored by both MITE and also British Council under the Newton-Ungku Omar Fund, or in short, we call it NUOF. So this project is basically a collaboration between Universiti Malaya, University of London, and also University of Southampton. So I hope I got that correct. So maybe just for everyone's general knowledge about NUOF. NUOF is basically a bilateral program between Malaysia and UK. The initiative started in 2014. It is basically a 40 million ringgit in collaboration per year. So under this initiative, we have about 28 programs altogether, ranging from capacity building, research, and also translational research in strategic areas that has been agreed by both UK and also with Malaysia. So after 6 to 7 years, North has been successfully producing many of positive outputs in Malaysia. One, basically, we have involved more than 1,500 people in the program. We have more than 1,000 citation. I think this will include your programs as well. More than 500 publications. And with regards to the industry linkages, we have more than 50 university and industry collaboration, because in translational research, we do have that requirement that industry needs to be part of the team to ensure that the product or innovation is commercialized. And from that, 28 plus IPs has been created and produced. And also 11 startups and spin-offs has been created. So maybe I can give one example. One of the program, Research Innovation Bridges, which was done quite a number of years ago, 2014. So that project is already ended. It took us about 3 to 4 years to do, and quite some number of funding that was allocated for that particular project. But due to the nature of it requires commercialization activity. It's the product now. It's one of the project is called Green Data Center. If you do have a chance, or maybe you are interested in that particular, you can always come to MITE to look at the product. It's in MITE. It's basically a submersified technology where we put the servers into in this specialized liquid to cool it down instead of using air condition. So those are one of those one of the examples that we have. And also just to share with everyone, another program on capacity building, we actually just brought back about 10 lecturers with innovation who have gone through what the program is called Leaders in Innovation Fellowship. Currently, it's now being rebranded into LIFT Global Program. So every year we would actually send between 10 to 15 lecturers with innovation to UK to learn how different types of model and entrepreneurship, because we understand some of the challenges that lecturers face when they create a new technology or new innovation. The next big question is, how do you actually link it with the industry? So this is one of a good program that we have produced. I think if you have heard about Robot Chikia, so that's actually one of our earlier participants, and now they're really doing really great, exporting to Mexico and such. So we do want to keep replicating those kind of best practices. So hence why MITE and also our international partners, we believe that we need to strengthen international collaboration, because no one person or organization or even a country can solve today's problem. With depleted resources and many new global challenges, we need to bring together our assets and also the best minds to provide solutions for many challenges we face today. So to conclude, I hope everyone who attends the conference will learn new things, build new bridges of partnership, and most importantly, ready to bring our local innovation to the next level. Thank you. Back to you, Prof.
Thank you so much, Mr. Ahmad Narazi, for taking the time to join us this morning. I think what you have said just now is very inspiring. I'm very sure this project will also be able to commercialize. We have an earlier talk with Smart Selangor, and we are in the process to communicate with JKR, our Public Works Department, and also KL. They want this KL City Council. So you should be able to be applied in the real world, and we are fine tuning the whole project to give on-site information of the landslide movement. And now I would like to invite our special guest, Professor Azizul B.M. Azizul Rahman from the City University. He has been very helpful with us, Universiti Malaya, out these many years that I know him, more than 10 years. He's been very helpful, very supportive, a man that we really appreciate. So I would like to welcome Professor Azizul, if you'd like to give an introduction of this project.
Yeah, thanks, Prof. It's good morning from Malaysia. Good morning from University of Malaya. It is our pleasure to be here at University of Malaya. And it's good to see that we are having a second international conference. During the COVID period, we did have lots of restriction. We couldn't come here for a long time, but the project has done very well. Thanks to MITE, thanks to Ahmed Razif for their support, and also thanks to British Council, Newton Fund for their support. And also we have a support from the Royal Academy of Engineering. And this particular project has gone very well. We have published several top tier journals, IEEE and other top journals. And also we have also got a one patent approved. So it has been very successful. And we have a long collaboration with Prof. Harith over more than 10 years. It started with PMI2 project, Newton project, British Council project. We are very happy with our collaboration with Prof. Harith. We also have our partner Ken and Co. Ken Gratton and Gilberto from Southampton. And also this particular conference is being supported by the Royal Academy of Engineering. And we have Aruplal Chaudhary Chakraborty from IIT India. Thanks for all for joining us in this conference. And let's hope that we have a very good 2 days of the conference. Thanks.
Okay, thank you very much, Professor Aziz, for finding the time to give this introduction. We do really appreciate your presence, flying all over, flying from UK, London to here. I think it's a big effort. We do really appreciate. I hope that Encik Ahmad Narazi is still in the conference. We hope for future funding of this project will be very helpful, Mr. Ahmad. Okay, now we can start the proper conferences. I would like to invite the first speaker, Professor Ken Grattan as the plenary speaker number one. I will read his short biography. Professor Ken T.V. Grattan graduated with a PhD in laser physics from Queen University of Belfast in 1979. Queen University of Belfast is a very renowned university in terms of laser physics in the early. From there, Queen's University of Belfast. Eventually, some of them moved to other universities in UK and also in Imperial College, and became a research fellow at the Imperial College of Science and Technology in 1978 to work an advanced catalytic driver for novel laser system. He joined City University London in 1983 and was appointed George Daniel Professor of Scientific Instrumentation in 2013 and to a Royal Academy of Engineering Research Chair in 2014. His research interests include the development and use of fiber optics and optical system in the measurement of range of physical and chemical parameter. He was elected as the president of the International Measurement Confederation, MICO, in 2014, serving from 2015 to 2018. He was also elected to the Royal Academy of Engineering and the UK National Academy of Engineering in 2008. He was awarded the Officer of the Order of the British Empire, OBE, by Her Majesty the Queen. And currently serves as the editorial board of several major journals in his field in the USA and Europe. From 2001 to 2017, he was the editor of the MICO Journal Management and also served as the General Counsel. He has been appointed the editor-in-chief of the Journal Management Censor in 2019. Professor Grattan is the author and co-author of over 700 referee publications in major international journals and a similar number of conferences, and is the co-author of 5-volume topical series on optical fiber sensor technology. His work is highly cited by his peers nationally and internationally. He also happened to be one of the project members in the landslide monitoring project funded by the Newton-Ungku Omar Fund. We are very fortunate to have Professor Ken Grattan as a member of this project with his very wide, illustrious career in optical sensor. As such, I would like to invite Professor Ken, if you would like to start your talk.
So thank you very much, Professor Harris, for the warm introduction. It's been a great pleasure to collaborate with our colleagues here at the University of Malaya for over a decade, and to have, I think, such a successful collaboration. And from that point of view, I'm sure we will hear more about that during the course of this conference. It's also a delight to be able to travel again and to be back with you in Malaysia. It's now been some 3 years since we were last able to do that. The world has changed. Lots of things have happened in the meantime. But one thing that hasn't changed has been the collaboration and also the warmth of the welcome here in Malaysia. So it's really good to be back with you. So let me share my screen and give you my presentation. So let's just see if I can find the right presentation. I have a habit of having too many. Let's just look at too many windows open at once. So here we are. So let's find the right one. Great, here we are. Great, so I hope that everyone can see my slides. And so the main purpose of today, sorry, I'll just get my, that's it, just get my own window here, correct? That's it. Good. So what I want to talk about in the half hour that I have is just something about the use of optical fiber sensors in industry. And what I thought I would do was just focus on the issue of sustainability and the ways in which optical fiber sensor systems can support the sustainable future that we are all concerned about. So in that sense, my aim was to give a few examples. And obviously, if anyone wants to follow up, be delighted to do that. Just give me a call by email. Hopefully, I can move to the next slide. It just takes a moment for this to load. I think it's just been a little slow to move on to the next slide. Make this move, I'm afraid. So just wondering if I should come out of it again and go back into it. Maybe the size of the file is quite large. That's stuck. Stop. Just wondering if I can. Let me stop presenting and then try again. Let's see if that's any better. Yeah, great. Good. So the idea really is to talk a little bit about sustainability and how optical fibers underpin sustainability. And I thought I would take as a reference the COP26 conference just held a few months ago, last year in the United Kingdom, which I think helped to remind us of some of the key issues. And sustainability is a particularly important issue for work in industry and for graduate education. But what I would suggest to you is that optical fiber sensors can have a significant role to play in this field. And what I want to do is give a few examples of where, from our own work, optical fiber sensors have made a difference in sustainability. And hopefully in that way, you can see some of the advantages of the field. So I'll talk a little bit about that, market directions and predictions, and then some future perspectives. And of course, international collaboration and cooperation really underpins the success of what we do. So this was COP26. This was what COP26 set out to do. And one of the key things behind COP26 is net zero by mid-century and keep temperatures under control. It's interesting that we're in Malaysia today. We have left London, and it's likely that London will be several degrees hotter than Malaysia. And climate change is very much blamed for the increase in temperatures in London and Europe. But in order to be able to make sure that we hand on to the next generation and the generation after that a real future on our planet, then we have to adapt to protect communities and our habitats. And of course, we've got to mobilize finance to do this as well. So basically, none of this happens without good links to industry and finance. Key thing is that I would suggest optical fiber sensors can be really important in this field. That if we work together to deliver, that we can really make a difference. And I think the emphasis, particularly at a conference, and a conference like this, is that working together really does make it possible to do things that we can't do separately. So in terms of sustainable technologies today, I think what I'd suggest as well is that we need connected, integrated systems in order that sustainable development can be monitored, and the changes that really relate to sustainability can help us to understand how we can do the right things for our environment. Obviously, the minimization of the waste and the reduction in materials, all of these come about through the fact that we can actually monitor. If we can make measurements in what we have, then we can start to make changes. And if we are going to improve our environment, if we're going to have cleaner production, then that's got to be associated with sustainable technologies. And we need technological innovation as far as that monitoring is concerned, in order to allow cleaner production to be brought about. So again, my main thesis today is that fiber optic sensors can make a difference. So what's the reason for saying that? Well, if you have a look at some examples that I would bring to your attention, this is just an illustration of a problem in a tunnel in Japan a few years ago, where basically due to the lack of maintenance, the lack of having a smart asset management system, and I'll explain a little bit more about smart asset management systems in due course. Basically, the tunnel started to collapse. Parts of the tunnel lining fell on the trucks that were passing through it, and basically the tunnel had to be closed. Now, this was a situation where it caused considerable inconvenience to both commuters and to people who were delivering goods, but a lot of costs in terms of the inspection that had to be done. A more serious problem was the collapse of a bridge in Genoa a few years ago, where when the bridge collapsed, there were 43 people who were killed as a result of that. It collapsed during a violent storm in 2018. And the interesting point here is that in this small cutout from the Times newspaper in London, you can see that the estimated cost of the disaster was between 4 and 7 billion euro or billion US dollars. And in that sense, the costs of these sorts of environmental disasters, which arise from the lack of maintenance and the lack of monitoring, are very significant. And the picture behind shows that the new bridge that's been built very quickly, but one that has been built with maintenance systems built in. And that has made a difference really in looking to the future. And an example again from London is the Hammersmith flyover. It's a bridge coming into London, and you can see a picture here of some of the reinforcement bars within this, which again was not monitored, not properly maintained, and it caused reduction in the strength of the building. And here you see the delays that were caused by traffic coming in. The bridge behind you can see is empty because it's unsafe, and here's the traffic that's been diverted, again causing major problems. So we have costs, we have the loss of life, and we have real inconvenience as a result of our infrastructure not being properly monitored. As well as that, the construction industry is one that really is a major challenge for sustainability. It plays a vital role in national economics, but it has a major environmental impact. And here's some data in terms of global CO2 emissions by sector. And you can see the big problems that arise from CO2 within the building industry. So it's an extremely significant contributor to global emissions. It's a contributor to the way in which our economies can move forward. But it's very clear that we have to look at ways in which we can monitor, and if we can monitor, we can reduce emissions, and in that way improve the situation. Just looking a little bit about aspects of the construction industry. What are some of the key factors? Well, if we look at where the issues around both operational carbon and embodied carbon exist, we have within the product itself, we have within the construction process, we have this within the use of the infrastructure that is produced, and both in terms of operation and maintenance and repair. And we mustn't forget end of life, that buildings don't last forever. They're often on very valuable sites, particularly in some of our major cities, where the value of the site is greater than the value of the building. And there are costs in terms of demolition and destruction, and there is a carbon footprint in terms of that whole process of removing a building. So from that point of view, it's carbon all the way through. And you can see here some of the data on the amount of carbon, both direct and indirect, across major countries across the world. And you can see that the effects are very, very significant. So my thinking really behind the discussion today is that we can monitor better through the use of optical fiber sensor systems. And we can develop optical fiber sensors for strain, humidity, temperature, vibration, acoustics, and so on. And this is something that we've done at City University of London, working with industrial collaborators. A lot of the sensors that we're dealing with operate on the basis of fiber bright gratings. And as I'm giving the first talk, let me just remind people of how a fiber bright grating works. This is just an illustration of the fact that if you take, let me just do this again, if you take light from a broadband source and then pass it through a fiber bright grating, you cut out a sample of that broadband emission at a particular wavelength, in this case, the orange color. If we then take the fiber and we stress it by applying, say, temperature changes, humidity, perhaps coatings and so on onto the grating, and then apply the same white light to that grating, we cut out a different color of spectrum, and you can see here the spectrum is shown in red. So although the color change is not quite as significant for a real device, this is illustrative of the fact that the color changes, the wavelength changes, and we calibrate that and use it as the basis of the monitoring that we do. So what have we been doing? So this particular talk is going to focus really around how good structural health monitoring can support sustainability. And in work that we have done at City, we have done monitoring of bridges, of foundations, of tunnels, and of wet concrete. And here you see some of the issues around foundations that we've monitored in a site in London. I think it just reminds you of the amount of a building that's actually below ground. It's both a significant cost, and it is a significant amount of time. And also, if you're going to renew buildings, remembering that these sites are extremely valuable. If you're going to try and renew buildings, then one of the questions is, can you actually use the part of the building that's below ground as well as the part of the building that's above ground? And even you demolish the part above ground, can you still use the building below ground? And again, monitoring of foundations makes a difference. But this again is just some sensors that we've applied to a special low-cost bridge, working with the Queen's University Belfast and with a company in Northern Ireland to create a special bridge. And these are just some of the sensor systems you can see here in the diagram on the right-hand side, which we used on that bridge to monitor both the strains on the bridge during construction and in use. So all of this relates to what I want to remind you of, and that is smart asset management systems, or SAMs, and suggest perhaps one of the important lessons of today is that fiber optic sensors play a key part in today's smart asset management systems. So civil engineering, as I've said, is a major contributor to global warming through additional carbon. It's also a field where there is real scope for more use of monitoring. And fiber optic sensors suit civil engineering very well. Remembering that fiber optics are low loss, and if you have sensors that are separated by meters, tens of meters, hundreds of meters, or even kilometers, then the low loss in the fiber means that you can set up fiber networks very easily. And just an illustration of some sensors here in a tunnel system. I think as well, what I'd like to suggest to you is that we need to take an IoT approach, an Internet of Things approach, because it's not just a matter of sensors, but of sensor systems. Also that the best results really come through interdisciplinary teams. I think what we'll find is that if you have teams that include professionals in the area, and we've worked successfully with, as electrical engineers and physicists, with structural and civil engineers and their industrial partners, that this really does make a difference. So often fiber optic sensors can be applied where conventional techniques don't work. And one of the key features really is that we need to see ways in which these devices can be operationalized in order to be acceptable to industry. And I think many of our universities have really taken that on board. And our collaborator in the University of Southampton perhaps is one of the major illustrations of how successful work done in the laboratory has been spun off into a number of companies, many of which have been extremely successful in bringing optical fiber devices to market. But in addition to that, of course, we still maintain our strong academic links. Our credibility comes often from the publications that we produce, and that is a balancing key part of what we do. But the message I would say to you is that we really need to converge and close the loop, taking us all the way from research through to operationalization of such devices. We've done a range of different things, looking at fiber optic sensors for the rail industry, for the power industry, for civil structures, for our transport, construction itself, marine transport, and indeed in structural health monitoring, and indeed in terms of civil infrastructure and monitoring for security. I don't have time to talk about all of these things, but again, just to show you something of the breadth that can be covered by this field. And on the chemical sensing side, I think one of the important things is the balance between both physical and chemical monitoring. We've done work in using chemical sensors to support our structural health monitoring, looking at high pH and chlorides. We have worked on ground monitoring in the ground, monitoring water, and monitoring the environment. Looking at heavy metals and water quality and pH, security, as I mentioned, and humidity and moisture applies in a wide range of applications. So I think perhaps it's not emphasizing, it's not just physical sensors, but chemical sensors that play an important part in structural health monitoring. And I think finally, just emphasizing the systems approach, that it's not just the sensors, but it's the sensors and the data, what you do with the data, how the data really are visualized and presented to the customer. The client that you deal with is really not usually too concerned about how the sensors work, but is particularly concerned about having the information that he or she needs. And in that sense, having information when it's needed, for example, for maintenance, and having information when, for example, there is a crisis is very important. So remember that the systems approach is key to success. Again, so mentioning some of the problems about reducing emissions from concrete, one of the things that we're continuing to do, working with UCL in London and Macrete, is a company that manufactures precast material, is microwaving of concrete. We've done some tests on this using small samples, applying fiber optic sensors, monitoring temperature changes, and setting up systems that will enable us to monitor successfully the changes in the concrete as a result of applying the microwaves to cure it. And I think the key thing that we have shown in this preliminary work that we have done is that you can produce concrete of the same strength as you can by conventional means, but with much lower energy. And the big advantage of using microwaves, which then, where you have fiber optic sensors to control the microwave oven, is that you can get that excellent monitoring of the temperature, so that you get exactly the temperatures that you want with the minimum use of energy. And we're just starting a new project to scale this up to the production of a range of different types of precast concrete elements. But for the last part of my talk, I want to talk a little bit about some of our collaborations in the water industry, how we've used optical fiber sensors to monitor in the harsh environments that you find in the water industry, in sewers, and in areas really where we're dealing with the challenges of an environment that's just not one that most sensors like. And I'll just take a few minutes as the end of this talk to talk about some illustrations of what we're doing. But above all, again, I think I would emphasize that we can only work successfully with a company like Sydney Water Company because we're actually producing interdisciplinary teams that enable us to meet their needs rather than to do the research that we want to do. The targets have got to be those set by industry. So just to give you an illustration, this is from Sydney, Australia, just a few weeks ago. And in fact, this is just outside the offices of the Sydney Water Company that we're working with in Parramatta in Sydney itself. And you can see the destruction caused by flooding, the river bursting its banks, and serious damage and so on. And one of the things that we've been looking at is whether, again, the sensor systems that we have produced are enable monitoring to be done that can help to alleviate some of the problems. And of course, I'm not going to talk about this in my talk, but just to mention the fact that landslips in Malaysia have caused major issues. And one of the successes of our collaboration with the University of Malaya, and I'm sure others will talk about it, has been the use of optical fiber sensors to alleviate some of the monitoring issues here. And in collaboration with the University of Southampton, I've just one slide here that illustrates some of that successful work that we have done over the last few years. And in particular, I think it's delightful to say that in spite of the lockdown and the difficulties in traveling, that we've been able to continue this collaboration and do some work and build some optical fiber sensors which have been installed in test situations here, and in that way to monitor and hopefully to help with the local problem of landslips. So in our work with Sydney Water, some of the things that we've been looking at has been to monitor pump stations, and these are Sydney Water has about 80 pump stations, some of which are over 100 years old, and they had a major collapse of one of these in 2018. So what we were able to do was to develop some fiber optic grating-based strain sensors to have these installed even during the time when we couldn't travel to Australia, and to monitor the situation and set up a SCADA system to enable monitoring to be done. And the main aim is to measure vibration and strain, and hopefully as a result of that, to ensure that we make sure that if there are any potential for collapse, that we can signal that in advance. And this is just some of the preliminary results that we've got from one of the pump stations. And you can see the data presented from 6 sets of sensors here that we have, showing the different compressive horizontal strains in the system. And really what we've been able to do is to give to our clients at Sydney Water information on what's been happening in the pump station, and to give them some confidence that there isn't going to be a problem with a future collapse. These are the results that we obtained over a 6-month period to March this year. Really what you have at the bottom here are just a series of strains from the sensor systems that are installed. And what has been good is the fact that we have a correlation with some of the changing weather conditions, and you can see the changes in the strain with time. But all of those strains are within levels that are perfectly acceptable. And in that sense, we've been able to say, to give confidence to our collaborator that the system is safe. We've also done some work on humidity monitoring in sewers. These are some of the sensors that we developed. And our commercial electronic sensor is one, the commercial electronic sensor is one that doesn't work well in these conditions long term because of the very acidic environment that there is. So we've developed a fiber optic based sensor, created a couple of different models and used those. And here you can see it in a sewer environment being tested and evaluated. And again, just to give you an illustration of the performance over a couple of weeks, you can see that it's been monitoring the effectively 100% humidity in that sewer for 2 weeks. The drop in humidity at the start and the end was done deliberately to show that the sensor retained its dynamic range, both at the start and the end of the tests. But I think what's important is, although you see on the left-hand side the calibration of the sensor, that here you see after about a month of exposure that the sensor still retained its integrity and still worked very well. Beside it, you see the commercial relative humidity sensor, which only lasted a week in this environment, and you can see the damage done by the acid corrosion from the gases present. And after 6 months, the situation looks even worse. Glad to say that our sensors are still working after 6 months, you can see the effect on the commercial sensor that it stopped working months ago, and really it shows that commercial electronic sensors are not well suited to this environment. Most recently, we done some work on anaerobic digesters, and we have put our sensors into a couple of stations here again in Sydney. And what we've been able to do is monitor the conditions in these tanks. Again, the situation is a difficult one because you have high levels of methane, which is explosive, carbon dioxide, which is dangerous to life, and hydrogen sulfide, which when it's wet produces sulfurous and sulfuric acid. And so these have been very challenging environments for conventional sensors, and we've found that we've been able to use our fiber optic sensors in these environments over some long periods of testing. And here just is an illustration of just the sensors being installed. You can see some of the challenges in putting them in installing the monitoring systems in safe and secure boxes in these environments. But we've been delighted that we've been able to get results over a 20-month period. This is work done just a couple of years ago, and you can see that what we have is monitoring of humidity on the left-hand side. The blue is one station, and then we switched the sensors to a second one, showing that the monitoring of the very high humidity in the 95 to 100% region. But the correlation with the yellow is correlation with the weather changes. And you can see that there is some correlation in the humidity levels in the digesters with the changes in weather. And again, when you look on the right-hand side, there's a very clear correlation with the changes in temperature as you go from the Australian summer in January through to the Australian winter in July, back to the summer again, and then for the Newton-Ungku station, again the last period in the summer. So again, good correlation in the results obtained. And our aim really in the next phase of this work is multi-sensor system, again used in the field. I'm running out of time, so I'm just going to illustrate the fact here that this is our plan. We're installing systems in a second station here, and we have worked with our colleagues to plan some 40 strain and 30 temperature sensors to be installed in this station, which is over 100 years old. So it's an interesting challenge to do this, and through a photographic inspection and inspection of the blueprint plans, we've been able to put together the planning. So finally, what's my message? Well, my message really is one of ubiquitous measurement. And I would suggest to you that rather like ubiquitous computing, ubiquitous measurement is this concept whereby we take hardware and software, and our aim is measurement anytime, any place, and anywhere. That we then aim that you can install ubiquitous measurement in a range of devices, in a range of situations, and with a range of formats. And really, again, so that we can ensure that we can use these measurement systems in situations that range from the industrial through to the healthcare, which are two very, very major areas. And again, industrial helps us with sustainability, and healthcare is vital really so that we can all live longer, healthier and better lives. And in that way, we can see that good measurement can be transformational. And again, I would suggest we integrate with the Internet of Things approach. So what's the key message? Work together to deliver. By working together, we can do more than what we can do alone. And I think our collaborations that we have had with a number of universities, particularly in Malaysia here and with the University of Southampton, and our collaborations with IIT in India in the field of monitoring. All of those have been really great illustrations of how we can do so much more together than we can do separately. So I would suggest cooperation brings real rewards and creates momentum, because these problems are not just national problems, but international ones. So what's my summary then? What is the way forward? So I think fiber optic techniques lie at the forefront of the use of sustainable technologies and sensing, and the solution to ensuring that we have a sustainable environment. In work that we have done, I hope in this brief review, I've given you an illustration of some good work in the optical and photonic sensors and how they can help in terms of sustainability, that spin-offs are really a key way forward so that industry can exploit the technology that we do in our universities in the long term. And industry benefits from this. Our graduate students benefit from it. We give them skills that they can take out and they can use in their future careers. Above all, the fields are interdisciplinary in science and engineering, and in that way we can create the new and better sensors that we need. The market is multi-billion-dollar, and it's a worldwide market. It's growing, and I would hope that I can suggest to you, in particular to some of the graduate students who are listening, that this is a great area in which to work, that it's an excellent area for high-tech developments. It's an excellent area in which to build your career, and an excellent area for really you're making contribution to the sustainability of this planet and your country. So let me thank you for listening. I hope you find this helpful. I hope you find it interesting. If you want to get in touch with me, then just send me an email, and happy to respond to that. But above all, let me encourage particularly the students, graduate students and early career researchers in this field. There's just so much to do. Stick with it and make your contribution to it. So thank you very much for listening.
Thank you so much. Okay, thank you so much for the talk, Professor Ken. I off my mic, yes, my apology. It's a very interesting talk being presented this morning by Professor Ken. In fact, we learned a lot of opportunity in optical fiber sensor. Maybe we can open for one or two questions from the audience. Is there any question? They are normally quite shy, Professor Ken.
Yeah, that's fine. If anyone wants to send me an email, if they have any questions, very happy to respond by email. So feel free to just email me any questions or comments, and I'll be very happy to get back to you.
Okay, if there's no question, I would like to take this opportunity to thank Professor Ken for a very exciting presentation. And we can go to the next speaker. Our next speaker for this morning, the plenary talk number 2, Professor B.M. Azizur Rahman. I'll read up his short CV for the audience for this talk. Professor B.M. Azizur Rahman is from the Department of Electrical Electronics Engineering, City University of London. Professor B.M. Azizur Rahman received his Bachelor of Science in Engineering and Master of Science in Engineering degree in Electrical Engineering with distinction. That is a very great achievement, with distinction from Bangladesh University of Engineering and Technology, a very well-known university, Dhaka, Bangladesh, 1979, respectively. He received his PhD degree in electronic engineering from University College London in 1982. From 1976 to 1979, he was a lecturer at the Electrical Engineering Department, where in 1998 he joined the Electrical, Electronic and Information Engineering Department of City University London as a lecturer, where he is now a professor. At the University London, he leads the research group on photonic modeling, specialized in the development and use of the rigorous full vectorial numerical approaches, frequency domain model solution, approach, the beam propagation method, and the time domain based on the numerical efficient finite element method. He is also a member of the Institute of Engineering Technology, which is IEEE, the Optical of OFSA, USA, and a senior member of the Institute of Electronic Engineering. He has published more than 450 journals and conference papers in the area of integrated optics, single polarization guide, photonic devices, power splitter, polarization splitter, compact band design, and many more. He's also one of the project members in the landslide monitoring project funded by the Newton-Ungku Omar Fund. Good morning to you, sir. I hope you have a nice morning. You may have arrived a bit late last night. Maybe soon you'll be experiencing jet lag. We will let Professor Aziz give his presentation now?
Yeah, good morning from Malaysia. Thanks for the kind introduction. I want to talk about, following Ken's talk, that what are the possible next generation of optical sensor, particularly I'll be focusing on more on compact optical sensor using planar photonic devices. So Ken has mentioned about fiber optics. I'll just mention briefly, but my focus is mostly on integrated optical based waveguides and sensor and their optimization, and then followed by sensor optimization. So if you remember that in old days in a optical fiber-based sensor, the particularly one was well established by surface plasmon resonance. You need to polish the one side of the fiber, and then you introduce a plasmonic or gold layer. And this was one of the pioneering technology used in 80s for optical sensing. Ken has talked about fiber Bragg grating sensor, and we have extensive facilities to make this fiber Bragg grating. And here there is a Bragg grating, and the Bragg wavelength depends upon the periodicity of air and also the refractive index change. And we have shown that, okay, now what is happening that if we want to use fiber Bragg grating for evanescent field, then there's a problem because in a fiber Bragg grating, the mode is inside the core, and it doesn't see anything on the side for surface sensing unless you etch the fiber and expose the cladding, or you can make a taper so the field is extended outside the core a bit, or the earlier one was polishing one side. So this is the way you can use a fiber Bragg grating either by etching or tapering or side polished for surface sensing. On the other hand, long periodic grating is also fiber based, but here the cladding mode is utilized, and the cladding mode, it will see something on the surface of the fiber. So for some of the sensors, long periodic can be used without etching, and in that case, the fiber is stronger and it has better stability. And we have done a work more recently using the long periodic grating sensing to detect heavy metal in water. We have a project with Indian Institute of Science and City University London. But the problem with fiber-based sensor happens that if I look at the fiber, and this is the cladding, as you start reducing the cladding, you are exposing the cladding for the sensing application. But still, if you can look at the left side, the percentage of the field, percentage of the optical power outside the cladding is less than 1%. And that's why what the people will do, you have to etch the cladding or polish the cladding. On the other hand, if you use a microfiber, if you reduce the diameter of the fiber, But if you reduce from 5 micron and come to 1 micron or even half a micron, only then you can see the field outside the cladding is increasing. And that's why the tapered fiber is also successfully being used for optical sensor design. But even if you think simple nanorod, simple tapered fiber, although it looks like very similar as optical fiber, but with a reduced dimension, but the solution is not that simple. It is not that simple is only because now the boundary condition at the upper and side interface are different, and that creates the problem. You can see that there is a structural symmetry, there's a rotational symmetry. However, the solution will not have a rotational symmetry. You can clearly see that HX field here is extending more horizontally and less vertically. And that is because the boundary condition of the HX field at the top interface and the side interface are different. Similarly, for the HY mode, it will be also different. So the circular symmetry is missing now because of the boundary condition. And also optical fiber base, there are lots of activities now using photonic crystal fiber. In photonic crystal fiber, you have lots of holes in the cladding area, and that allows access to the evanescent field much better than the simple optical fiber. So the photonic crystal fiber is also being used for optical sensing. And you can see that optical fiber in the model, this is the field inside the core, and you can see that it's trying to come out in between the two holes. And also the field in the ear holes will be much stronger than field for simple optical fiber. Another sensor has been used, is called surface plasmon sensor. An earlier generation, there is a prism and there is a metal layer, and then used to launch a light, and this at a particular angle, it will generate surface plasmon mode, and that was used for plasmonic sensor. And today, many of the very well established optical instrumentation, they do use this sort of scanning technique and planar metal mode. However, metal thickness and the metal width, they are comparable, and most of the modern advanced plasmonic sensor, then the mode is very, very complicated. The reason is that you have a plasmonic mode at the upper metal dielectric interface. You have another plasmonic mode at the lower interface. You have a plasmonic mode on the two sides. And they started coupling, and that coupling depends upon the height and width. And what you can see here is the range of the mode, very, very complex, and you need a very, very strong modeling technique to identify this mode. So similarly, the plasmonic mode can be also used for optical sensor, fiber-based sensor, or integrated optic. But one thing you have to see that once you have a metal coating, the field inside the core can be isolated from the field outside the core. So there is no interaction of the inside the core mode with anything happening in the outside, unless you can link this inner mode and the outer mode. And how can we link it? You have to think of the plasmonic mode. The upper interface of this metal layer and the outside dielectric, there can be a plasmonic mode this interface. There's also another mode, can be inner side from this metal mode, this metal, and the inner dielectric. These two modes, there are two plasmonic modes, they can only interact with each other, they can only talk to each other if they have the same or similar phase velocity. And that's what you need to do. You need to optimize the devices, optimize the dielectric so that the mode inside the core and mode outside in the cladding are phase matched. And that we work here. And you can see that there are two modes. One is the outside, one is inside, called super mode. And they only interact when this dimension of the metal is about 30, 40 nanometers. And in that case, you can interact so that something is changing outside will interact with the mode in the inside. And this mode, you can see that now I have solved only 1/4 of this waveguide. But you can see that although the fiber, it was metal coated circularly symmetric, but the solution is not circularly symmetric. The reason is that in this case, I'm solving HY mode, that's TA. The boundary condition of the HY field at the right interface between the dielectric and the outside is different than the boundary condition at the top interface. And here you can see there is no field at the top interface, but the strong field in the side interface. And if you look carefully, like here, if I now plot the field along the horizontal, what you can see here, you can see a field like in the inside is showing there's a metal interface, there is a plasmonic mode, field is decaying inside exponentially, field is decaying outside exponentially, and there is a dip. And this dip is typically is called even like super mode. And even like super mode in plasmonic guide is less lossy than odd like super mode. And that's why it is more often used for optical sensing. And here what we tried to adjust the cladding thickness and the material so that there is a place where the fiber mode, which is the horizontal line, the plasmonic mode, which is the line coming down like this. At this position, their betas are similar, and that's where they interact. And that's the time, that's the area we should be used for optical sensing. And what you can clearly see that this left side is the odd super mode. This one is a even like super mode. And when you go far away, then these two super modes are isolated. Whereas at this position, you can see they're clearly interacting. And this is the way you need to optimize a metal clad fiber sensor. Following that, we have done quite a different sort of work. You have a core, you have a trench, you have a nano metal rod, you have and what we're looking at, I'll show you this slide later on. I'll explain to you that also the multiple of nanorod you can put there, and also you can put a metal coating. And we have compared the sensitivity for different cases. Now, if I focus on this figure, the red line, this red line is the dispersion for the plasmonic mode, which is, you can see, reasonably steep. The black line is the dispersion for the core mode, dielectric mode. What you can see here is that this time they're crossing. Actually, they don't cross. What they call anti-crossing. That anti-crossing is showing on this side. This is the dielectric mode. This is plasmonic mode. This is the plasmonic mode, the pink one continuing. This is the dielectric mode on the left, and another dielectric mode there. There is an interchange jump happens. So this is the dielectric mode where the modal loss is less. The other side is a dielectric loss mode, which is modal loss is less. But at this area, because it is interacting with the plasmonic mode, so the loss increases rapidly here. And what you can see, the loss curve, loss is low, increasing rapidly, and then again reducing. So this is the rapid loss at that particular point is utilized for optical sensing. And this is a much more expanded field profile showing in the metal layer in the dielectric mode. You can see their coupling, not only coupling, what you can see here, how along the vertical line, if I plot the field, this peak is a plasmonic mode, and this is the dielectric mode. And from that, what we look at the resonance variation with the refractive index. And what you can see here, that sensitivity of with the plasmonic nanorod is much higher. The slope identifies the sensitivity, and this is a thin metal, uniform metal coating. What my focus has been, I want to do is more compact photonics sensor. And for that integrated optics, there has been different work, has been Mach-Zehnder, Fabry-Perot, Young interferometer, dual mode. I'll briefly talk about some of them and what is the future. So briefly, a Mach-Zehnder mode, what you have a laser, split them to two, and then combine to two. If the path lengths are equal, then they combine in phase and you get the output. However, by putting a sensing layer here, if I can control the refractive index in the sensing layer, then the phase velocity will change. And so the phase of the two incoming mode will differ. And that's why the output one will depends on the refractive index change here. And that is the basic principle of maxillary interferometer. The modern these days, instead of the Y junction, I think MMI-based splitter is much more compact and much more better. And that's we will consider it. But in any sensor design, particularly in evanescent sensor, most important thing is that to exploit the evanescent field and how we can expand that. We'll talk about that, and particularly in the context of the planar waveguide. One interesting thing was found in, say, 10, 15 years back is called slot waveguide. In a slot waveguide, the basic physics is that the continuity of the dn, and that what it makes is a normal component of en is a discontinuous. And if E2 is 10 times smaller, then En2 has to be 10 times bigger to satisfy this boundary condition. And so what happens that at the low index area, that is E2 epsilon 2 is smaller, then E2 has to increase. So the smaller index field is higher, which is contrary to like a Snell's law total interference reflection. But one thing you have to understand that this is only happens to the normal field, only to the normal component, not to the tangential component. And so you have to choose a mode where normal component at that interface is the dominant component of the mode. So what happens if the slot is a vertical, then EX is normal to this, and that's why it will work with a T mode, and you can see the very high field in the vertical slot. But if the slot is horizontal, then EY will expand in the low index area, and that's why it will only work for TM mode. So this is a very sort of novel idea that in a low guide index area, particularly in a void or in an opening, you have higher field, and it allows access to the sensing material or light matter interaction in that area. The slot area can be filled up with either electro-optic for modulator or gain media for amplifier. But for sensing material, we can put either air or water or blood and to design a very, very powerful optical sensors. So the way you can fabricate a horizontal sensor, because you have to have a gap here, which can be either air or water, so that you can have a sort of cantilever arrangement, and silica can be etched in this area to open up that one. And then you can coat with a biosensing material to have a good optical sensor. That we again optimize and simulated, and quite often in the slot area, you can get 40–50% of the power confinement using single slot, and we optimize the design to see that at what sort of dimension width and the slot width, you get the best performance of the sensor. But as I mentioned that the slot is very, very polarization dependent. Horizontal slot only works for TM, vertical slot only works for TA. So what we looked at is a cross slot. So that what you have a horizontal slot, you have also vertical slot, and it can be supported by a cantilever arrangement. In this case, you can have both T and TM mode simultaneously in this slot. So this is showing a simulation showing that HY field, HY or EX field is here, and EY field in the horizontal slot. We can optimize in a way so that this line is showing the ratio on this one showing as 1. That means T power and TM power is exactly equal. And what we're showing here by a proper design, you can have a 39% of the power in both TE and TM simultaneously in the same slot. So this slot waveguide is now quite widely being used, not only for single slot, but here we are showing case of 3 slots. And so that you have more fill, 60–70% fill in the slot. Another thing came also recently is called sub-wavelength grating. You have a grating like fiber bright grating, but it's a sub-wavelength. The period is much smaller than the period. And if that happens, then you can see that it behaves not like a grating, but behaves like a homogeneous waveguide with a reduced refractive index. And what it does, it opens up, because this gap can be air or it can be water. So you have a waveguide where you have an opening of the air and the water, and you can have a much more better sensor than having a simple waveguide-based sensor. So now what we are considering in a proposal saying that, can we then incorporate both sub-wavelength grating along the Z direction and also slot in the horizontal direction? And in that case, we believe the sensitivity of the sensor can be much, much higher. We haven't done this simulation yet, but this is the thing we are hoping to do in next. So now this sort of waveguide, now we can introduce in a Mach Center or any other structure. And we hope that we can have a very, very like a most advanced optical sensor probably we can think using the Mach Center approaches. We can also have a plasmonic slot. In a plasmonic slot, you can have a metal either upper or lower, and then another high index dielectric. In between, you can have a mode which is known as a plasmonic slot. So it takes the advantage of both plasmonic and the slot configuration simultaneously. And we have done some simulation, some early work for a gas sensor using porous zinc oxide. Is a low index area where the gas can be filled up, the metal on the top, silicon, looking at the mold and optimize it. And I think time is running out, so we'll move quickly. And what you can see clearly, this is the clear sign of plasmonic peak at the porous zinc oxide and the metal interface. These are the plasmonic peak of the plasmonic modes. And again, we optimize this design. And what we're looking here, more than 41% of the power is in the slot to get the best design. Another work we did is a resonator, but not a ring resonator, but a straight resonator, where we have a short length of the waveguide, which works as a resonator. But in this case, this short section is not a standard waveguide, but a slot waveguide. And this we simulated because of the resonator problem, we have to build up a different computer program to analyze this. And again, what we looked at the sensor design for using a slot waveguide. And we optimized this and again published it. We also work on asymmetric, hybrid, plasmonic, Mach Center-based interferometer. Not only that, also what we look, because the loss in the two branches are different, we used different power splitting ratio in the power splitter so that we get a better imaging contrast in this design. And again, what we looked at that, how much delta C coming from different sort of isopropanol concentration. So briefly, there's also young interferometer, which is similar as a Mach Center, but instead of continuing it, you have two waveguides, and this then forms an interference pattern, but it needs a CCD camera for the sensing. There's another sort of new design is coming called bimodal interferometer sensor. In Mach Center, if you think there is two branches and you're sending this light through two different branches and their phase velocity, one of them is different because of the presence of the sensor. In a bimodal, what happens? You have a single mode is coming. You have a structure which can support two modes. So this single mode is generating the two modes, first mode and second mode, is going through the waveguide and combining. But what is happening, whatever be the sensing layer here, their phase velocity changing for the mode 1 and mode 2 are different. And so that delta phase at the end of this bimodal section depends upon what is there in the sensing layer. And that is being used, so very compact design is a bimodal interferometer. And what I have been thinking is that I can consider instead of bimodal, instead of the first mode and second mode, I can think of a first mode and third mode. If I use a MMI structure, and if I use a symmetric excitation, this will not generate second mode, but will generate first and third mode. So that's the first idea. Second thing, if I use sub-wavelength grating, then you have a higher field in those slots. Then if I use the 2 slots horizontally, and what you can do, you can optimize the location so that the peak of the first mode and peak of the third mode, because remember third mode will have 3 peaks, and that we can try to control the position so that you got the highest delta beta between the first mode and the third mode. Briefly, the ring resonator is a simple and very, very compact sensor you can design using ring resonator. And one thing is that suppose you have a ring resonator, the wavelength will go through and will depends upon the resonating condition, resonating mode number, because at a particular wavelength, we'll have an integer multiple of the wavelength along the circumference. But if you have a sensing material, it shifts. Okay, and that's how we identify the sensor. And what people are now already using is that in the ring resonator now, instead of a simple ring, you're using a slot waveguide. Not only that, people have used plasmonic slot, vertical slot, and also some cases the ring has been suspended. It is supported in the middle, but the ring part is suspended, and that's how you are getting much more better sensor than simple ring resonator. But also there are other way work of resonating disk, supporting whispering gallery mode, and plasmonic nanoparticle, 3D resonator. These are the future state of sensor for the next generation. And the ring generator, as I said, there can be much more complicated design. You can have this area which can be used for sensing. You cover the whole area so that only this part is the sensing area. You can add ring resonator with the Mach Zehnder. You can add the ring resonator with Mach Zehnder and Sonic loop. And these are the way next generation of sensor can be developed. And main thing is that whatever be the sensor, whatever be the with the ring resonator or slot, you have to have some sort of selfing mechanism. So if you have filled with a biomolecule antibodies, they can attach to the waveguide randomly, but we need to have it selectively so that what we can have, if you have a antibody is you coated, then a particular analyte will match it, and so it will be very, very selective. And so only you can see that this one is adding, so only it can identify. Other thing, if present or not, it wouldn't influence it. So the main thing is coming very strongly is a biofunctionalization of the photonic sensor, and the protein, enzyme, peptide, DNA can be used for functionalization, and that's how we can generate it. So, and the conclusion is that what I'm trying to talk about the concept of the next generation of optical sensor, particularly using planar integrated optic based. We are happy with the collaboration we have been doing with Dr. Harith Ahmed over more than a decade. And thanks to all of you for joining this conference.
Thank you so much, Prof. Aziz. A lot of new ideas for the student and also for the members here. I think we may need to talk to you about, we are trying to do this nanowire. I think this Dr. Anwar and Firdaus may want to sit down with you to get a better idea on this evanescent field. That is a very exciting presentation. We will open for 1 or 2 questions before we break for tea. Is there any question? Somehow our audience, Professor Aziz, never ask question. I don't. Sometimes I'm just wondering why. Can we take any question?
Yeah, I'll be happy, but if they feel shy, they can email me and Ken, and we can discuss with the student if they want, or we can discuss during the tea time if they're here. If they're not here, obviously lots of student people are attending from outside. They can email us.
Yeah, about 67 attendees today. We have about 200 over, but for this morning 67. So thank you for your time, Professor Aziz. I will see you for tea in a few minutes time.
Where's the tea? Will be in this building or your building?
No, it's in your building, the one that you saw along the corridor.
Okay, thanks.
Okay, I will see you shortly, Professor Aziz. Thank you very much. This is the stop of the first session this morning. We will continue back at 11:45. Bye bye.
I think it's here tea. Oh, sorry. It's good that
Is it working now?
Yes, it does work.
Ah, great. That looks like it's well done. So how did you do that then? To just
I'm not sure
So
I've done it yet.
I think you're
Stop sharing. Yeah, so something is happening.
yeah, because I think you're sharing.
Do you see the slides?
There's some
Yeah. Okay. Assalamualaikum, Prof. Aruf. Are you ready? Are you okay?
Yes, I'm ready. Could you please check if my presentation is visible? I'm going to present it now.
Right. Okay. So welcome everyone to our.
Is it on full screen mode now?
Okay.
No. Okay.
Session for plenary talk of second international conference on innovative optical sensors. I'm Salina Zakaria, and I'll be doing chairing this session, which will be from actually 11:45. But anyhow, we can start now, and I would like to introduce our plenary talk by Prof. Arup Lal Chatuboti. Am I pronouncing it correctly, Prof?
Chakraborty
Chakraborty from Electrical Engineering, IIT.
Gandhinagar.
Yeah, right. So I would like to read a little bit of Prof. Arup Lal biography. Prof. Arup Chakraborty received the Bachelor of Technology degree in Electronics and Communication from the University of Kalyani, India in 2000, and a PhD degree from the University of Strathclyde, Glasgow, UK in 2010. He's currently a professor with the discipline of Electrical Engineering, IIT Gandhinagar, India. He also leads a photonics sensor laboratory that has a diverse set of interests that are underpinned by near-infrared and mid-infrared tunable diode laser spectroscopy techniques. Okay, Prof. Arup's group, interdisciplinary research, is directed toward industrial process monitoring and safety, microbiological and nanobiosensing applications, environmental monitoring, and biomedical sensing. He's all worked on distributed optical fiber sensor at the Raja Ramana Center for Advanced Technology, Department of Atomic and Energy in Indore, India, from 2001-2007. Prof. Chakraborty also senior member of Optica and a member of Optical Society of India. He's also a member of awarded the Distinguished International Associate Award for the Royal Academy of Engineering UK in 2021. He had published over 80 papers in ISI Index Journal, in which they are highly cited by his peers nationally and internationally. So here I would like now, without any further ado, we would like to turn the time to Prof. Arup. Screen is yours, Prof.
Thank you, Professor Rosalina. Very kind of you to introduce me. I'm into the full screen mode. Could you please confirm that it's visible?
Yeah, it is full screen.
Full screen. Full screen. Thank you. Thank you. I'm delighted to be here in Malaysia. This is my first trip here, and the warm welcome has been overwhelming. It's great to travel after 2 years of COVID, so we are all very excited. I'm here to speak about some interdisciplinary applied research that is currently going on in our lab in Gandhinagar, which is in the western state of Gujarat in India. We are a relatively new institute. This is what it currently looks like. It's about 10 years old, and we are on a very green campus next to a flowing river. So my invitation to anyone who would like to visit. The current group members are here on the left, some PhD students who are relatively new, and some postdocs. We also have a successful group of alumni who are distributed in academia and industry. Among collaborators, I have Professor Grattan and Professor Rahman, who've just spoken, and I have a couple of collaborators from our own institute. And we are funded very generously by both Indian agencies as well as the Royal Academy of Engineering, and especially I'd like to thank the Distinguished International Associates Program that has allowed me to travel to this conference. My talk is divided into the following four 4 sections. I will talk about tunable diode laser spectroscopy as a very, very powerful gas sensing technique. Then I'll talk about some applications of TDLAs. First, for environmental monitoring in Ahmedabad, which is the city that I live in. This is an applied area of research. And then I'll talk about some more, a little bit of a fundamental study in microbiological growth. And then I'll talk about a fiber Bragg rating based activity that we have undertaken. The need for very precise, reliable gas sensing is shown over here. There are a large number of areas in which you need to monitor gases to detect gas leaks, and as well as to monitor how much of a gas is produced. And these situations come with their unique challenges. So these are all outside the laboratory. So any technique that you develop within the lab must be easy to translate to the field without compromising on the reliability of measurements. In red, I depict the challenges that each of these areas throws up, and you will see that the main challenge is the harsh environment that is not protected by the laboratory conditions. The light has to traverse through dirty environments. The optics and mechanics has to deal with fouling due to dirt, vibrations, and there are also interfering species of gases that could throw your measurement off. So we need to quantify, not just detect. Detection is a relatively easier task, but we want to measure exactly how much the mole fraction is. And in some cases, we also want to measure the pressure and the temperature using such remote measurements. Professor Grattan has emphasized the need for such field measurements, and I'll show you some examples of what we are doing with it. Okay. Conventional gas sensing systems have their own limitations. They are either based on oxidation and reduction, or something is being burned, or in the case of the gas chromatograph, the gas has to flow through a eluting fractionating column, and in solid state you have absorption. So these come with their unique challenges, the main challenge being either slow response or cross sensitivity to different gases, or the sheer bulk of the system. So none of this is really applicable for the kind of applications we are talking about. So very briefly, what is this technology all about? The idea is very simple. You take laser diodes whose wavelength is tunable, but they emit a very, very narrow range of frequencies. And the wavelength can be tuned using either temperature or the current. And you pass this light through a molecule that's vibrating and rotating. And if you choose the wavelength correctly, you will be able to induce these rotational vibrational transitions in the molecule. And you will see, as a function of wavelength, that the molecule absorbs at certain discrete frequencies, discrete wavelengths. And there is a shape of each of these lines. And it turns out that if you can extract one of these absorption lines, you can extract information about the gas, namely the mole fraction, the pressure, and the temperature. The good thing is a large number of molecules leave their fingerprint over this mid-infrared region of the electromagnetic spectrum, starting from 3 going to 14, and now it's gone up to 20 microns. And there are a large number of lasers that you can use to address some of these lines. Now, there are so many molecules, so is it possible to detect one of them in isolation? So if you look at this picture, it shows that there are a large number of absorption lines, but there's a lot of overlap as well. So you want to avoid this overlap so that you're not confused about which molecule you are detecting. So a closer simulation shows us a combination of ammonia, water vapor, and carbon dioxide. And in this application, you're trying to detect only carbon dioxide. So there is a lot of overlap, but if you see this red line encircled in green dots, this line is relatively free from water vapor and from ammonia. And so this is the wavelength you would preferentially choose if you wanted to measure carbon dioxide in the presence of water vapor. And that's a great example because outside in the atmosphere, you cannot control the amount of water vapor. So you can be blind completely to water vapor and detect only carbon dioxide. The technique is very simple. You take that one of those tunable lasers, you control its current and its temperature, and then you set up 2 photodetectors and a detection system, and you start the laser. When there's no gas, you get a straight line like this. The variation, this line shows the variation of the laser's intensity. And when you put in a sample, you see a wavelength selective behavior over here. And this is the signature of the molecule. This is one of those absorption lines that we showed earlier. The trouble is that this is a time indexed data because this is an oscilloscope or a data acquisition system you're using, and you need to convert from the time to wavelength. So you put in an echelon, which is basically a resonating structure. And as Professor Rahman had reminded you, the resonating structure has peaks and troughs as the wavelength is varied. And this spacing of these wavelengths is constant and very, very well known. So you have 2 signals, both of which can be superimposed one on top of the other, and therefore you can convert your raw time index signal into a wavelength referenced spectrum. So finally, you have the entire spectrum of carbon dioxide, in this case, being measured at mid-infrared wavelengths of 4319 nanometers. And if you simulate this absorption line, and once the fit is good, you can extract the mole fraction, the pressure, and in some cases, the temperature as well. So you have detected the gas uniquely in the presence of water vapor with high precision. You don't require an optical spectrum analyzer. And the most important thing is this measurement is absolute. And that's something not appreciated well enough. This instrument would not require you to calibrate. And that's because you are recovering the absorption line directly. Now that is fine, so the method works, but it has limited sensitivity, right, because it's essentially a DC measurement. So we modify this slightly and bring in an additional modulation into the laser's current, and you do exactly the same thing. You pass the modulator laser through the gas, and you detect one of the harmonics. You have to introduce a lock-in amplifier, and you modulate at a frequency, you detect at that frequency or its higher harmonics. Again, the idea is simple. You have the direct absorption line, and you're modulating in frequency. So those of you who are from the communications background will recognize that frequency can be converted to an intensity modulation if you have a spectrally varying transfer function. So the gas absorption line is a transfer function in this case, and the local slope is going to be, you're going to extract the local slope. So if you modulate at FM and demodulate at the same frequency, we call this 1F detection. And this is the shape you would get. And this roughly corresponds to the first derivative of the gas absorption line. If you modulate at FM but demodulate at twice FM, you get a signal that's called a 2F signal, and it's roughly again the second derivative. Now the good thing is that second derivative sits on 0, so you can amplify the signal without amplifying any background. The 1F signal does not sit on 0, so you have limited scope for amplification. Now this is all well known. Won't go into the details. Just going to go into some measurements, remembering that we are going to use either 1F or 2F. So the signals you will see will look like this, and we will extract the gas parameters from these signals. Okay, I'm going to proceed a bit quickly. So as you know that the carbon dioxide levels in the atmosphere are going up. Currently we're at 416, 17 ppm already, and some of the underdeveloped countries or the developing countries have higher levels of pollution. So we wanted to measure how how much CO2 there is in the atmosphere, and Gujarat, being a very highly industrialized state of India, emits a lot of pollutants. So we wanted to take a look at the urban situation in Gujarat. So this is all part of the Global Atmospheric Watch program that monitors CO2 all over the world continuously. So we have our reference at 416. When we were doing this work, the value was 400 parts per million. So this is where we are located in the western state of Gujarat, and we chose a couple of locations within the city and decided to check certain claims made by our civic authorities. So we built a system. This was the initial system. There was an app that could send you the data. And this is a typical Indian footpath where the pollution is maximum. So our system sat on this footpath for a whole day at each of these locations. And thanks to the perseverance of the students, we've got some really decent, useful results. So this measurement was for water vapor as well as carbon dioxide, and at 4 locations. This is version 1 of the system, a roughly 28 centimeter path length. The light interacts with gas molecules that come into within this path. So finally, we did some laboratory validation first to check our detection sensitivity was good enough. The detection sensitivity was about 70 parts per million. And we have, as you see on the right, the signals are pretty good. The noise level is not that bad. And then we took the system out for in-field measurements. And on the left over here, you see the data that we got on the footpath. The alignment was had to be made very carefully so that the signal to noise ratio was high, which it is in this case. And this gave us confidence to extract the mole fraction. And this is what's depicted here. The red line, the dotted red line shows you 400 parts per million. That was the global average at that time. And you see the campus of our institute is closest to the 400 million ppm, but other parts of the city are way, way above. Now, this data is not captured currently in the pollution monitoring instruments that are there in the city. So we believe this is the first time that's been done, and we believe it's time to scale it up. So we scaled it up, and we wanted to compare the situation in a city with the situation in a remote hilltop, which was far away from urban sources. So we built a mid-IR version of this system, took it up to this place called Mount Abu, and we did a week-long measurement over there. And then we came back the following week, we made measurements in IIT Gandhinagar and compared these two values to see if there is a difference between urban values and background values. That is an indication of how well the cities are doing with respect to the background. So on the top, you see the CO2 values are hugging the 400 ppm level over a week. But the following week, measurements in IIT Gandhinagar, remember, it's a green campus. In there itself, it's 500 parts per million with quite a bit of fluctuations. So this makes us believe even strongly that deeper into the city, the situation will be much worse, and it requires sensing. So we've validated our measurements carefully, and we've found that the detection sensitivities that we've got meet and in some cases exceed the sensitivities recommended by the World Meteorological Organization. So that gives us confidence that we can build more such systems and make reliable measurements. This technology was also in partnership with the Defense Research R&D organization, DRDO. It was transferred to an onboard oxygen sensing system. So we're glad that some of this work has gone out of the laboratory. So that's rather pleasing. The current project that we're working on, in which Professor Grattan and I are collaborators, is this work. There are 2 projects actually that's funded. And the idea is to miniaturize the system and make it possible to put on a UAV. And that could be flied around at various locations in the city so that we can map pollutions not just on the ground level, but also take it up and see how the vertical, how it varies as you go up and down. So the system is currently in this shape. We fully expect it to become further miniaturized, and instead of the camera, we're going to fit the instrument over here and then do some flight tests. Initial measurements on ground are very promising. As you see on the right, the signal to noise ratio is good and the fitting is very good. The entire system is remotely operated from your laptop, and it can be as long as you have Wi-Fi access. So that's our main activity, but along the way we also came across this interesting work in which one of our students realized that microbes put out a lot of gases. And antimicrobial resistance is a huge problem now. People have used antibiotics rather freely, and we're beginning to feel the bad effects of that. So it's important to monitor microbial growth, and if you want to suppress it, you have to measure how they're growing. The growth mechanism is well understood. So the microbe initially doesn't grow, then has an exponential growth, and then it tapers off and it dies. So the point is, if you can measure somewhere early in this exponential growth phase, then you can possibly think of inhibiting the growth by different means, either by drugs or by other means. So the key is to try and detect growth early, rather than wait till the growth has progressed too much. That's where the challenge is. Traditional methods are slow. 16 to 48 hours is the incubation time before you get a value. So it's you really need rapid detection. So we were asking, could this tunable diode laser method be used? And the setup is very, very simple. You have a laser and you have a detector, and you have the microbe growing in this broth, in this closed container. And as it grows, it respires and it puts out carbon dioxide in this headspace. And we're just curious to measure the carbon dioxide and see what pattern it shows. So when we did these measurements, we found out we were again targeting one of the absorption lines, and we saw that the relative transmission was growing as time progressed. And when we plotted the mole fraction of CO2 as a function of time, it showed the same kind of sigmoidal S-shaped curve that theory predicts. Please note that the x-axis is very, very long, up to 10 hours. So conventional methods would wait up to 8 to 10 hours before you could detect measurement. But clearly, we can detect measurement within an hour or two, and possibly sooner. So that's definitely an advantage. We tried this with another variant. This is S. aureus, a really bad bacteria, and that too showed the same kind of behavior. We were able to detect much early. So we have these good points: non-invasive, there's no sample preparation, which is an annoyance. It's non-destructive, so you don't need to interrupt the growth. It's real and rapid, real-time and rapid. So 2 to 4 hours would be considered ultra-rapid. 8 to 10 hours is considered rapid. So this demonstrates ultra-rapid detection. That's something we need to scale up. And very quickly, a student was also doing an interesting study on light-emitting bacteria, and we saw that the light emission on this right-hand panel, if you see over here, the black line shows the growth, and there is a specific period of growth where the light emission begins and peaks. And interestingly, this period happens to be the highest growth rate period. So this is very interesting behavior that we observed. And finally, once you've detected the growth, you would also like to check whether the growth is suppressed. So a student used some antibiotics over here, ampicillin in this case, allowed the bacteria to grow and applied different doses of antibiotics as per recommendation, starting with no antibiotic and taking it up to 5 microgram per ml. And she was able to see this drastic reduction in growth. But the interesting point is not here, not at 10 or 12 hours. The interesting point is that even within 2 hours, you are able to separate the red line, which shows no growth, and the blue, black, and green line that show growth. So if you were using a drug, you could claim that you'll be able to detect suppression of growth well within 2 hours. So your overall antibiotic testing could be speeded up this way. And this could be applied to a non-drug scenario as well. So we believe there's some potential here. So that's all for the gas sensing part. And I'll quickly go through some FBG. How am I doing for time, Dr. Rosalina? Just a quick indication, please.
Yes, Prof. I think you can just finish yours. It's about
5 minutes.
Yeah, 5 minutes. Yes, Prof.
Yeah, thank you. That'll be fine. So we did some work on the fiber Bragg rating, and there are 2 activities. One is a glove that's meant for stroke rehabilitation. Another is a microphone. That's just interesting. So stroke is a big problem in India and in some other parts where rehabilitation is essentially not a very well guided phase. So it's boring to do some certain exercises, and the patient doesn't have concrete evidence, concrete feedback about how well he or she may be doing. So, and it requires a lot of intervention by rehabilitation doctors and rehabilitation staff. So one of my students took this up, and it was essentially a curiosity-driven exercise. He was taught the physics of the fiber Bragg rating that was discussed earlier, and the student was then encouraged to try this out, stick the FBG onto a finger. I don't know why the video is not working, and just monitor the fiber Bragg rating reflection spectrum as the finger was bent. Yeah, it's working now. So I'll let the video play. So as the finger is bent, the strain induced at the joint, and the fiber Bragg rating is now shifting with the angle. So you can measure this shift, because that green trace over here is again the frequency scale of the resonator. So you can relate the angle by which you bend to the spectral shift of the FBG. So he put it into 10 of these joints on a glove. I'll show you the design later, and then interrogated all those joints simultaneously with a commercial interrogator. This is the final glove. This glove has 10 FBGs embedded in it. And we found some very good results, that the strain response was linear, which is very important. There was no hysteresis, and the linearity was preserved for all the joint angles and for a large number of participants as well, who are using the same glove. So it was not a customized glove for each person. So the strain response being linear makes the glove easy to calibrate, and the dynamic response was also excellent. We compared it with the inertial measurement unit, which is very commonly used to measure angles, and we found that the dynamic response of the FBG was much superior compared to the IMU, as the speed of rotation increased from 5 degrees per second to 80 degrees per second. The IMU showed these undershoots and on the leading and the falling edge, but the FBG did not show any distortion in the shape. So that was a very important result for us, because the exercises would become progressively, as the patient recovered from stroke, the speed of rotation would be faster and faster. So that gave us a lot of confidence. We got it validated by certain experts who are sitting in the same room as I am now. And the results have been better than competitive. Some awards came along the way, which was very pleasing. And that prompted Chandan to interface this with virtual reality. And so currently he has a startup in which I hope you can hear these piano sounds. As you bend the fingers, you can play certain games. You can also play music. So he is actually doing tests with patients who are recovering, and I'm told that the feedback has been very, very good. The glove went through a couple of design iterations to make it robust. That's why the effort of the students is involved. Just a few pictures of the same thing here. Currently, you can play a game on a tablet, and it can give you scores. you can increase the difficulty level, you can customize the game. So there's a lot of flexibility in the VR environment, and this has to be advised by the stroke specialists. So there's a loop that we want to create where we are doing the FBG stuff. There's a patient and there's a doctor who can give us feedback on how things are going. So that's more or less it. I'll end it over here. We're rather pleased that we had this OFC demo zone. We were able to show this. We got a bit of nice feedback. So overall, that's all we have. I guess I've run out of time, but I can just maybe hopefully quickly play this video over here. The fiber Bragg rating being sensitive to strain makes for an excellent microphone. So very quickly, you will hear Chandan speaking into this fiber Bragg rating microphone with a lot of background noise playing on YouTube. There's the mobile camera is also recording his voice, but the sound on the mobile camera recording is very poor, but the FBG records the voice very clearly. Currently, you're not able to hear anything he's saying because that's the mobile phone's recording. The signal to noise ratio is very, very low. So in a minute, in a minute you will hear what the FBG recorded. Right now he's going to play it. Here it comes. So these were artillery commands. If recognized incorrectly, you could be shelling your own men. So the FBG has tremendous noise suppression capability, and we believe there's some way to go with this project. So thank you very much for your attention, and I'm happy to get in touch with anyone who might be interested. Sorry if I've taken a little more than the scheduled time.
Thank you so much, Prof. Arup. It's very interesting, very informative, and I'm quite impressed with your presentation. Right, so I open the floors for any questions from the audience. Any question? Right, Prof, I have one question to ask you about the microbial growth. You know, that experiment
Yes.
that the microbiology, micro growth. Yeah, how do you enhance the sensitivity of your bacteria? Any functionalization process to enhance the sensitivity? And how is this process?
No, the bacteria are not, they are left to themselves. We don't do anything to the bacteria.
Right.
And that is an advantage because there's no sample preparation. So the bacteria doesn't need to be given anything special. It just needs to be given its natural food, which is the broth shown in this picture. And you let it do its own thing. And so the measurement is completely non-destructive, non-invasive, and there's no sample preparation. So that is an advantage.
Oh, right. Okay. Thank you so much, Prof. It's very impressed. Right. Thank you so much, Prof, again for your presentation. And it's a thank you again. And okay,
thank you very much.
Thank you, Prof. Right.
Unshare my screen. Yeah.
Right. Okay. We have another session by technical presentation by Muhammad Junaid. Do you, Muhammad Junaid, are you here?
Yes, Prof. I am hearing.
Right. Okay. Muhammad Junaid, are you ready for your technical presentation?
Yes. Yes.
Right. Okay.
Doctor.
All right. Okay. Without further ado, okay, you may proceed.
Doctor, can you hear me?
Okay, yes, I can hear you.
And the screen is clear, visible?
Yes, I can hear you clearly. Where are you now in engineering?
I am at University Malaya.
Okay, right. Okay. You may
Can you
proceed.
see my screen? Can you see my screen?
Slide. Not
Yes.
yet. No, not yet.
Okay.
Yes, now I can see your slide.
Assalamu alaikum and good morning. This is Mohammed Junaid. I'm from Integrated Lightwave Research Group at Faculty of Engineering in University of Malaya. Today here I want to present my research work, Novel Plasmonic Monomer Array for Refractive Index Sensing using FDTD method in Second International Conference on Innovative Optical Sensor 2022, organized by Universiti Malaya and in a collaboration with City University of London and University of Southampton. And before going to my main presentation, I want to outline all of my topics, which basically I want to describe. First, I want to describe about the motivation and background of this research, and then the main objective of this work, and then the methodology, what I used to this, and finally, I want to describe about result and conclusion. Plasmonic biosensor play a very vital role in disease diagnosis and the development of innovative treatment drugs. Especially this type of biosensor detects viral particles, antigens, nucleic acid from clinical specimens. And there are many advanced technology, nanotechnology provides this methodology to develop selective biorecognition elements. And fundamental principle of plasmonic biosensor rely on the surface plasmon resonance technique. So now I'm talking about the principle of surface plasmon resonance technique. Surface plasmon are basically coherent electron oscillation that forming along the interface between thin electric metal film and the dielectric medium. So this type of excitation can overcome the diffraction limit, and we can easily control and manipulate it in the nanometer scale, the propagation of light, or we called it in sub-wavelength scale. So there are normally two types of this surface plasmon resonance. This is called localized surface plasmon polariton and propagating surface plasmon polariton. And in propagating surface polariton, there are two types. This is called, one is called asymmetric and another is called symmetric. And this strong enhancement of LSPC is very suitable for refractive index sensing, source measurement, and biomolecular detection. So when the surface plasmon and the incident light, their energy and momenta are the same and matched, then a resonant condition is created. So this resonant condition is strongly dependent on the refractive index of the dielectric medium. Therefore, even very small changes in the refractive index will produce a measurable shift in the resonant depth. So here there are some background study of plasmonic nanohole array architecture. So in previous, there are some work have been done on monomer, dimer, trimer, quadrumer, heptamer, and hexamer. So in first 1998, TW Edison observed this extraordinary optical transmission through sub-wavelength nanoholes. Then in 2014, Jan et al. Presented a nanohole quadrumer in FEM method, and which is basically suggest a coupling mode between dipole quadrupole modes or two antiparallel dipole modes. And after 1 year, 2015, Gina et al. Described this heptamer and hexamer. And in 2017, Akram et al. Used the same method for plasmonic gold heptamer arrays. In 2022, Stephen Sanders have briefly described the dimer plasmonic nanohole and the monomer plasmonic nanohole. So the main thing is existing plasmonic nanoholes has a lower bulk sensitivity and figure of merits. So a novel plasmonic nanohole structure is should be needed, which has high enhanced sensing resolution and offers rapid and level-free biosensing. So our main target is to design and simulate unit cells of the plasmonic nonamer array. The nonamer means there is 9 holes, 9 plasmonic nanoholes, and this is come from that. And to study the changes of refractive index of different analyte layer from refractive index 1.33 to 1.37. So we are doing this methodology to with using finite difference time domain method and numerical solution ink software. So then first we use propose geometrical modeling and use some physical parameter, and we have to set the simulation region, and we has to use some different mesh technique for appropriate values, and then we use source and monitor, and we finally get the result. So all type of analytical solution are not suitable for this type of solving this photonic structure. That's why there are many numerical methods are applying, and finite difference time domain method is very useful for solving this type of problem. And we use ANSYS numerical solution software. So this is our proposed unit cell of 3D plasmonic nanomer. If we look at picture A, we see DC is the diameter of central hole, and DS is the surroundings holes. And there are 1 central hole and 8 surrounding holes. So the structure is consists of total 9 holes, and it is called nonamer. And the top layer, we use different analyte layer or cover layer. And then there is gold layer, and then is titanium layer. Titanium layer is very useful for adhesive layer. And there is fused silica. We use fused silica. And here px is the periodicity of the unit cell in the x direction, and py is the periodicity in the y direction of this unit cell. Normally in this structure there are lots of plasmonic nanohole. This is plasmonic nanohole array, but we normally simulate only the single unit cell. And the distance between surrounding holes to central hole, this is 30 nanometer. And if we consider the radius, this is 170 nanometer. So when we do any performance characteristics of plasmonic sensor, we use bulk sensitivity as a parameter. So it is defined as the shifting of resonant wavelength relative to the change of refractive index of the cover medium or our analyte layer. And another thing we also characterize, which is called figure of merit. It is defined as the sensitivity between spectral line width of the resonant peak. And in our structure, we count as the Fano peak, and the deep distance is known as the spectral line length of the resonant peak. And here, this is our transmission spectrum at different refractive index. So for simplicity, we normally use the only one peak. We calculate this picture, and when we change the refractive index, the wavelength is shifted. So how much wavelength is shifted in response to refractive index? This is then we calculate the sensitivity. So this is a close view of this first peak, only our proposed peak, and we said that there is a changes of wavelength. So from this calculation, we found the bulk sensitivity is around 437.5 nanometer per refractive index unit, and the calculated figure of merit is around 88.07. So here we can compare our work with our previous work. So we see the bulk sensitivity, the highest found from nanohole dimers, 486, and our nonamer also 437. It is also quite good. But the main thing is our figure of merit is extraordinary. We got it around 88.07. So this is an ultra highly sensitive novel plasmonic array, what we presented. And the transmission spectra support multiple asymmetric phenotype resonances. And our proposed nanohole structure has a bulk sensitivity of 437.5 nanometer per refractive index unit, and a figure of merit of 88.07. And in the future, we will calculate all the transmission peaks. And additionally, we use surface sensitivity we will calculate the surface sensitivity of different biomolecule layer or a different layer. And we can use this structure to be integrated in optical fiber tip for different biosensing application. So here are some references, and thank you.
Okay, thank you, Junaid. Yeah, if I pronounce
Yes.
it correctly, Junaid. Yes. Okay.
Yes.
Right. Is there any question from the audience?
Thank you very much, Junaid, for your nice presentation. Actually, I would like to know, did you use any analyte for sensing, biosensing?
Okay, in our proposed structure, we use analyte from different refractive index, such as from 1.33 to 1.37, different refractive index of analyte. We don't mention particularly any analyte. We just calculate the total spectra from 1.32 to 1.37, because I think there are lots of analyte which is in this category.
Okay, thank you very much for your
thank you.
Nice
thank you. Thank you.
Thank you. All right. Okay, I have a question, Junaid.
Sure.
Okay, right. I found out the FDTD results that you presented on your slide 15, on the slide 15, right?
Okay, sure.
Yeah, on the slide 15, it seems like so good, to be honest with you, because you have different parameters of refractive index from 1.33 and 1.37.
Yes.
And this is, I bet this is using FDTD simulation, right? Yeah.
Yes.
Yes, okay, right. Have you tried run this experiment? Have you get any, like comparison with the experimental and simulation result?
Basically, we are doing only simulation things. We are not doing any experimental work.
Right. So how are you going to clarify that your simulation can be used to sense any biosensing?
Okay, for biosensing, real life biosensing, we can use surface sensitivity. We can add additional protein layer or different layer. So this is our future work. Basically, we are not covered this conference, but we can do this as a different layer, surface sensitivity. So we can calculate this thing.
Right. Okay. All right. Okay. Yeah, quite interesting, because in my lab we are doing experimental. We're not focusing on the simulation, but it's good to know that if you can prove that your experimental result we can get as good as in the simulation, so we can have a good agreement between simulation and experimentals. And findings. Yeah, I just want to know. Right. Okay. Is there any more question from the floors? Okay. If no, I think thank you again, Mr. Junaid. I wish you best of luck in your experiment, in your work. Okay. Thank you.
Thank
all
you.
right. Okay, this will end our session this afternoon, and thank you everyone for joining this session today, and I hope to see you again in the next time. Thank you.
Oh, kau tahu ni? Ha. Three S apa? Anggap dia proposal ni. Ha.
I think who's the chairman for this session? Lim Kok Seng, eh? Prof. Aziz, are you there? Prof. Aziz?
Something opening. It's crazy. Absolutely none. And then the lights come on, light provide line there.
Aziz is sitting now.
What burning fish?
Shall we start?
Yes, Prof. Aziz.
Yeah. There's a reflection.
Yes, start if you want. I think this echo could be the TV is on.
There can be a reflection, maybe.
Okay, is Ashraf there? They're supposed to solve this reflection.
Yeah, so well, I think because both of us we have to on, so I will. So you reduce it and then I'll start, then you start. Then I'll move. Okay, good afternoon. Welcome to this session of the second international conference on innovative optical sensor. It is a pleasure. It's my pleasure to introduce Professor Gilberto Brambilla at the University of Southampton Optical Research Centre, one of the leading research center in photonics in the whole world. And Gilberto has been with Southampton University since 2016 as a co-director and general manager of the Future Photonics Hub. He has been director of the Center for Information Innovative Manufacturing in Photonics until 2015. He also leads the research group, Optical Fiber Sensor and Devices. He obtained his MSc Engineering with honors from Polytechnic Milano in 1996 and PhD from URC in University of Southampton, 2002. 2007, he was awarded the Royal Society, very prestigious Royal Society Research Fellowship. He has published more than 400 papers in the top international journals and conferences, and authored 8 patents and given more than 50 plenary, keynote, and invited talks in all the 5 continents in the world. He's also the project partner with University of Malaya on the landslide monitoring project, as we discussed in the morning, which has gone very well. Please, Gilbert.
Thank you very much, Prof. Aziz. Now I'm going to share my presentation. Thank you very much for the organizers for inviting me, and particularly to Dr. Kari. And I will start my presentation on optical fiber sensors and the challenges that we're going to face in future optical fiber sensors. I'm probably pushing an open door, but I want to stress the importance of photonics. Photonics is in pretty much anything we do, and we use it from laser biomedical to welding cars, imaging, defense. And so it's very important in modern society. And this is a graph that summarizes its impact in the British society, where it's worth £13.5 billion to the economy, employs 69,000 people, and it has a growth of 4.2% per year, so 8.4 over 2 years. So why optical fiber sensors? So this graph shows the global optical fiber market, and you can see telecom represents approximately 40%. But the remaining 60% is mostly optical fiber sensors. So optical fiber sensors represent a significant fraction of the optical fiber market. And most of people forget that indeed the first application of optical fibers was in the 50s, well before optical fibers were used for telecom, and this was the endoscope. Now, there are lots of different optical fiber sensors, and it's quite common to classify them in intrinsic or extrinsic according to whether the fiber is used as a sensing element or is just carrying light. And if we have a look at the intrinsic, then we can divide the optical fiber sensors in point or in distributed sensors. And we can go forward and basically further classify the point sensors in gyros, which is possibly the most famous point sensor, magnetic field sensors, and gratings. Could be used for biochemical, physical, strain, and temperature measurements. And similarly, the distributed sensors can be divided according to their physical mechanism in Rayleigh, Raman, and Brillouin sensors. As far as distributed sensors are concerned, also the detection system is important because that constitutes a significant fraction of the business. So I'll quickly have a look at the extrinsic sensors, meaning the endoscope, and see what the future can hold for us. And I think it's quite widespread, the feeling that on the long run, what is going to happen is the long wavelength shift of endoscopes to do thermal imaging, and multicore fibers like the one that you can see in this graph are supposed to work in the mid-infrared. Good pixelation, so good arrays, of course, is important for IR imaging. The problem is the fabrication of that, because we need to have tens of kilometers of fibers with this well-defined pixelation. And one possible solution is the use of chalcogenide glasses with fluoride polymers coating. If we go down into point sensors, gyro is definitely one of the most successful sensors. And the reason is that it is used in airplane navigation systems, in UAVs, and even in ballistics. And if we have a look at this graph, which represents the optical fiber sensors versus the competition, we can see that the optical fiber sensors that are within the dashed red line include submarine navigation, air lens in navigation, and even torpedoes and flight control. So it covers all the most important fractions of the market. And indeed, this is stretching in every direction to cover all possible applications. If we have a look at the fiber gyroscope, basically this is a Sagnac interferometer, and there are two modes that are propagating. One is in the same direction as the rotating system, and the other one is in the opposite direction. And the phase difference between the two allows to determine what is the rotation speed. If we look at the system, it looks more or less like this. So we have a source which injects light, goes through some optics, and then there is a splitter. So light is divided, half goes through the coil, the fiber coil in one direction, and half goes through the fiber coil in the opposite direction. The two are then recombined and go to the detector. Then there are some electronics, and the output is from the demodulation. But the important part here is the coil, the fiber coil, which actually is the sensing element of the gyro. If we want to go to higher sensitivity, instead of using this open loop configuration, we can go to a closed loop where the output of the modulation is put into a servo and into a phase transducer, which modulates again the light going into the coil. But even in this configuration, the coil is the important bit. This table represents a summary of various gyros commercially available, and the best performing gyros are the ones close to the top, which have the better bias instability, the smallest bias instability, and the smallest angular random walk. What is important is that to know that if you look at the length here, the fiber length increases, and for best performing gyros, there is a longer length of fiber. So the message here is that very long fiber lengths are needed for the best performing gyros. Now, there are some limitations, and the most important is the backscattered radiation, because this induces noise between the propagating and the counter-propagating beams. The optical care, because the optical care effect can change the optical path and therefore induce an intensity imbalance, which can induce an error again in the monitoring of the rotation speed. The thermal fluctuations that induce still the different delays in the counter-propagating modes, and polarization and birefringence. In the past, these have been addressed using a low coherence light source, which solves the top two problems, using a particular winding on the bobbin, specifically called quadrupole, and using a specific type of fiber, the PM fiber, which basically looks like this. This is a cross-section of fibers. There is the panda fiber on the left, or the bow tie fiber on the right. There are two stress rods next to the core that basically make a polarization that is along that direction feel a different effective index with a polarization with orthogonal direction. Now, for the future, it seems that there is an alternative solution to this, which is a hollow core fiber. And why is that? Because there is smaller attenuation. In fact, the best results published now show that hollow core fibers have lower attenuation than telecom fibers. There is very small nonlinearity, so a small Kerr effect, and there is negligible backscattering. So this might be the fiber of the future for the gyro applications. The problem is, how do we fabricate tens of kilometers of this? Our hub has been working on that, and what we've done is scaled up the preform. Here on the left, you see the size of the preform that went from 1.5 millimeters up to 5 millimeters, and the length of fiber that was drawn from these different canes increased from 400 meters to 12 kilometers. So from the manufacturing point of view, it's a significant challenge, but can be solved. And the next step is go forward and reach hundreds of kilometers from peripherals. Another type of sensor that is interesting for the point sensors is the magnetic field. And these rely on the Faraday effect. So we have fiber of length L, and there is a magnetic field parallel to the fiber. If we inject linearly polarized light along, let's say, the vertical direction, when the light is propagating inside the fiber, experience a rotation, and the azimuth of the polarization rotation, theta, is related to the magnetic field, to a property of the material called Verdet constant V, and the length over which this overlap happens. Now, this has been exploited to measure currents. And indeed, in this configuration that you see in the bottom right, we have a relation between the theta, so the polarization azimuth rotation, and the current that is propagating inside the bus around which the fiber is coiled. So this was commercialized by a Swiss company. Where is going to be the future development? In replacing the fiber possibly with a tapered fiber. And why is that? Because we can measure very short pulses. So this is, for example, a nanosecond pulse with the rise of 6.7 nanoseconds and a fall time of 6.8 nanoseconds. We have also demonstrated sub-nanosecond pulse widths. So this seems to be of interest for EM detection, EM pulse detection and countermeasures. The other very successful point sensor is the grating, of course. Grating, as you can remember from the first plenary talk, is basically an interference of a constructive interference of different reflections. And we have a relation between the pitch of the grating and the Bragg wavelength. So these are manufactured using a face mask. So we have a UV laser that is hitting a face mask, and the interference of the UV laser beams on the fiber produce a spectrum that basically is wavelength encoded. And this means that we can actually collect several gratings with different wavelengths, lambda 1, lambda 2, lambda 3, and use wavelength division multiplexing for interrogation. In other words, we have a broadband source that is injected into the fibers where the Bragg wavelength, the Bragg gratings are multiplexed, and the reflected wavelengths are then going to the spectrometer. And interrogations are typically in the region of 1 kilohertz speed. The typical way to make a cheap interrogation is to use an edge filter. So the detection happens using a coupler that splits into the arriving power and an edge filter that basically converts the wavelength is intensity. Can this made cheaper? And that is what we're working at the moment. This is what we are working on, a scattering chip wave meter, which is essentially a glass slide with some dots on it, a camera, and a Raspberry Pi electronic. So all of these cost less than $20. And then we have a collimator for the optical part. So this spectrometer is less than $100, and most of it is actually the collimator. So this seems to be a very cheap way forward. How do we make this? We use femtosecond laser. We pre-randomize dots that we write into glass. So this is one layer. The next layer will have slightly shifted dots, and the next layer again. So we have lots of layers of different shifts, and the light basically is scattered at different positions, and these positions are wavelength dependent. So by mapping the scattering positions versus the wavelength, we can actually reconstruct the spectrum from this very simple geometrical design. Now, there is also another way to interrogate fiber Bragg gratings that is not with wavelength encoding, but using the time encoding. So we send a pulse, And the pulse that is reflected at the first FPG will go to the detection faster than the one that is reflected in the second FPG, simply because there is an additional time that is spent for the pulse to go from FPG1 to FPG2 and back, and so forth. So in time, we will have a collection of peaks that are related to each of these peaks. This is called optical time domain reflectometry. And there is space to make FPGs cheaper using this interrogation technique. I will talk about it later. But what I want to stress is that there is a strong interest in developing FPGs because it's using structural health monitoring, like you have seen in the first talk by Professor Grattan. And in aerospace, for example, for the composite fuselage of the airplanes. This is, for example, a wing testing facility, if I well remember, at Airbus in Spain. And you can have it in buildings as well, like this one, for example, which is the Canton Tower, which has 208 FPG sensors multiplexed within the tower. So there are lots of applications for FPG sensing. And one of the most recent is 3D shape sensing. So there is a support rod, which is the circle in the center, and fibers that are stuck by epoxy to this rod at 120 degrees. When the rod is bending, then it is possible to determine the geometry because the stress experienced by each grating is different. So a new approach would be actually to replace the three single core fibers with a multi-core fiber like here, because in this case, we don't need to use epoxy. We don't have problems with delamination related to epoxy detaching. And this could be a way forward for the shape sensing that use gratings, like in this case, for bending measurements. I now move to the distributed sensing part. Distributed sensors are probably the most successful amongst the optical fiber sensors, and they represent nearly 50% of the market. And the reason is very simple. If we consider connected to the data acquisition system via cable, so if we have 1,000 sensors, we have 1,000 cables. For distributed optical fiber sensors, we have one system and the fiber that acts as a cable. Therefore, the cost per unit of sensing is very, very small because we don't have 1,000 electric cables that connect the data acquisition system to the sensor. What we get is just a time-dependent intensity response. And if we look into distributed acoustic sensing, what we have is actually a reflection of a pulse that is propagating to the fiber at one interface and at the second interface. And when the two recombine, they can produce an interference that is constructive. But if there is a bit of stretching, the interference between the two scattering parts is not, for example, destructive. And by monitoring the phase difference, it's possible to determine what is the elongation experience between these red and green parts. And therefore, if we look at the time dependence of this elongation, the vibration or the acoustic sensing. This is a schematic of the setup that we use. So we have an optical part, which is basically the pulse generation, a sensing fiber, and then we have a detection unit that has an amplifier because the signal involved is small. And this is how it looks like. We have detectors in the top part. We have detectors in the top parts and the electronics at the bottom. So this was the second generation of our unit, portable, that traveling into Japan or the Philippines. What do we use it for? This is subsea cable monitoring, so power cables subsea. And we measure the vibrations in these cables. For example, when the anchor is dropped onto the cable, or in this case, so this is an anchor that is dropped onto the cable, and this is the oscillations that are time dependent and basically vanish within 5 seconds. Or a cable oscillation, like you see in the top graph. where you have a continuous oscillation of the cable up and down. We used it for railway monitoring, like in this case. So we have a cable attached to the rail, and we can monitor the train moving on top of it. We can move, for example, we can monitor even the track that is underneath. So we have lots of information that is coming from the acoustic monitoring. And we developed the unit even further, and this is our third generation. So this is approximately about 15 kilos, and it's slightly larger than a desktop computer. And it has a sensing range that is 45 kilometers. We deployed it in Muroto to monitor earthquakes and tsunami. So in Muroto, there is a DONET system that is a collection of sensing units that are connected by optical fibers. We use one of these for our sensors. So this is the building where there is the unit, and we have the fiber that goes underwater. So this is the building, how it looks like in Japan, and here is where the fiber goes underwater. So here you can see what sort of environment the fiber is. And you can see that there are continuous waves that come onto the shore. And this is what we recorded versus distance. And I want to show you what happens in these few hundred meters close to the shore. So this is basically the distance along the y direction and the time. And each of these is a single wave. So this is a wave that is at the distance, let's say 1,500 meters at this time. And then it moves close to shore versus time. And at this time is 900 meters away. So each of them is a single wave. And we can track waves during normal weather. During stormy weather, we can see also that the wave profile is different at different distances. Here, for example, you have a different behavior of waves than this one. So there is an issue, though, that is the signal that we get tends to become small and smaller and smaller. And at 50 kilometers, it fades away. So there is a signal fading problem. And that's the reason why we have two amplifiers in the system. Now, there have been different solutions to improve this. One is to have gratings that are manufactured on the tower. They're called Bragg grating fibers. And they have a loss that is typically in the region of few dBs per kilometer and produce a signal enhancement of 30 dBs. So having this type of fiber at the end can extend the range between 4 and 20 kilometers. What we have done is to have an enhanced scattering fiber. So we induce the point scattering points that have a loss that is smaller than 8 dB per kilometer and induce a signal enhancement of 17 dBs. So this new fiber can extend the range of 24.3 kilometers. How do we fabricate them? We use a femtosecond laser. So we have a laser, we have some optics, and this is focused into a fiber. And by writing, we have these nanostructure fibers that increase the back reflectivity of the fiber. We have a 20 dB signal enhancement, and the loss that we measure is in the region of 0.1 dB per kilometer. So overall, this means that we can extend the sensing range by 66 kilometers. So from 45 to 100 kilometers. And this is quite important. We made measurements together with the help of the US Naval Research Lab. And we have seen that actually the signal to noise ratio, so this is the phase noise, in the fiber, in the telecom fiber, and in the fiber with reflectors, show 30 dBs difference. So this fiber can provide a strong signal that is represented by this signal that is comparable to the one in normal telecom fibers, but a noise that is 30 dBs lower and works over a large range of wavelengths. ESFOS is the company that we set up to commercialize these fibers. Now, there is also another application to go even further And we managed to reach 152 kilometers using this type of fiber. And why is this important? Because there are situations like, for example, border monitoring, where you have to build a little house to host the equipment when you want to monitor fiber. And if you can sense 50 kilometers, you need to have one house every 100 kilometers, because you can go 50 kilometers on each side. If you can sense 150 kilometers, this means that the location of these houses where the system is hosted is going to be spaced every 300 kilometers. So there is a factor of 3 saving in the building investment and so forth. It's a significant investment. Now, this is the result that we achieved in the 152 kilometer single access of DDR. And as you can see, there is a clear signal at 151.4 kilometer with respect to the background. We still have 20 to 30 dB signal to noise ratio here. It's a strong signal to noise ratio. And why did I say that this could replace gratings? Because these are cheap. Are essentially less than £1 per grating, per reflector. And gratings in comparison are between 50 and 100. So this is a way to make grating sensing system a factor of 10 cheaper. What is the issue? The issue is that you need to fabricate these fibers, and it's time consuming. So in conclusion, I would like to summarize my talk saying that the optical fiber sensor market is a significant market, and it's continuously increasing, and according to some estimates, is in the region of $4 billion per year. So although there are lots of competition, there is lots of competition from other sensors, the optical fiber sensors tend to have an edge because the cost per sensor is small. Optical fiber sensors include lots of different types of sensors, and they've classified according to whether they're intrinsic, extrinsic, point or distributed, and what sort of application they have, strain, temperature, rotation, and so on. But as far as the manufacturing challenge is concerned, the challenge is always to make them faster, cheaper, and better. And before I conclude, I want to thank all the funding agencies and the people in my organization that contributed to this presentation. Thank you very much. If you have any question.
Thanks, Gilberto. Thanks for a nice talk. And if there's any question from the audience. I cannot hear anything. So if you have anything, you can always email to Gilberto. And you can get all the email from the conference organizer.
I will be happy to reply. Thank you very much.
If not, we can move to the next speaker.
Thank you.
The next speaker is Sir Yasuki Mizuno. Yasuki Mizuno received his BEng, MEng, and Doctorate of Engineering degree in electronic engineering from the University of Tokyo, Japan in 2005, 2007, and 2010, respectively. In 2012, he became the assistant professor at the Tokyo Institute of Technology, Japan. Since 2020, he has been an associate professor at the Yokohama National University, Japan, where he is an active fiber optic sensing, polymer optics, fiber fuse, and LiDAR. He has authored more than 178 approved papers and has given more than 50 invited talks at the international conference, including OFS and OECC. He's a senior member of the Institute of IEEE, Photonics Society, and a member of the Japan Society for Applied Physics and Optical Society of Japan, and the Institute of Electronics, Information, and Communication Engineering. Now, the floor is open for the Yasuka Mizuno.
Okay, thank you very much. Can you hear me? Is my slide okay? Okay.
Yeah, we can hear you.
Okay, thank you. Okay, thank you for the introduction, Chair. I'm Yosuke Mizuno at Yokohama National University in Japan, and I'd like to express my gratitude to all the relevant people for providing me with the opportunity of this presentation. And today I'll be talking about a bit strange topic on a so-called fiber fuse phenomenon in plastic optical fibers and its application to sensing. Okay. And this is the outline. After introducing the background and the purpose, I'll talk about the fundamental characteristics of plastic optical fiber fuse. And then I'll show some microscopic images and discuss the propagation mechanism. And then I present its application to sensing, especially to magnetic field sensing. And finally, a conclusion will be given. So let's start the background. Well, I'm sure most of you know that Brayron scattering in Brayron scattering in optical fibers can be used to develop distributed strain and temperature sensors. In Brayron sensors, using Brayron frequency shift, strain magnitude or temperature change can be derived. And today, let me skip the detailed explanation of Brayron scattering itself. And to date, Brayron scattering properties have been studied not only for silica glass fibers, but also for specialty glass fibers such as chalcogenide, bismuth oxide, telluride, photonic crystal, or multi-core fibers. However, before our first success, there had been no reports on the observation of the Brayron scattering in plastic optical fibers. And plastic or polymer optical fibers are composed of acryl-based materials like PMMA, and they have large core diameters ranging from 50 to 980 microns. And consequently, they are multimodal fibers with a step index or graded index profile. And their propagation loss becomes lowest at visible wavelengths, but the low loss window can be extended even to telecommunication wavelengths by perfluorination, namely by replacing the hydrogen in acryl with fluorine. And when used in sensors, plastic fibers offer numerous advantages such as low cost, easy connection, high flexibility, safety, and memory effects. But we will not go into their details today. And this table summarizes the Brayron scattering properties of silica single-modal fibers and perfluorinated plastic fibers. The amount of the Brayron frequency shift in plastic fibers is about 4 times lower than that in silica fibers, and which indicates that the plastic fibers are very soft. The Brayron threshold power in plastic fibers is extremely high, which indicates that the Brayron signal in plastic fibers is quite weak. The coefficients of the Brayron frequency shift dependencies on strain and temperature indicate that the Brayron scattering in plastic fibers can be used to achieve highly sensitive temperature sensing with less strain sensitivity. And we've already succeeded in demonstrating plastic fiber-based distributed Brayron sensing with a high signal-to-noise ratio and high spatial resolution of centimeter order. And we've also achieved the higher speed operation and dynamic strain sensing. And we are now working to improve the performance of plastic fiber-based brilliance sensing further. Then, this slide explains the motivation of plastic fiber fuse research. As I've already mentioned, brilliance scattering in glass fibers is extremely useful. But glass fibers are easily cut or broken even by small strain. Therefore, we are now focusing on brilliance scattering in plastic fibers. But the brilliance signal in plastic fibers is extremely weak. So what should we do? The simplest solution is to inject high power light into plastic fibers. But in that case, an optical fiber fuse phenomenon is generally induced. So what is optical fiber fuse? An optical fiber fuse is a continuous self-destruction process of a fiber. If high power light is injected into a fiber, the fiber is locally heated and the optical absorption is raised. Then an optical discharge, or plasma as is usually claimed, is initiated, and it propagates towards the light source, consuming the light energy and destroying the fiber. The fuse propagation velocity in glass fibers is generally about 1 meter per sec. The fuse is now considered to be one of the limiting factors of the maximal power that can be delivered in the fiber. Therefore, the fiber fuse creation should be avoided. And in order to do so, its properties need to be well clarified. And here I'll show you a movie of the fiber fuse propagating along a silica glass fiber. As you see, the bright spot is traveling very fast. The light source is on the right hand side. And to date, the properties of the glass fiber fuse have been studied and well clarified. For example, the propagation velocity is reported to be in meter per sec order, and the threshold power density is 1.2 megawatts per square centimeters, corresponding to several watts injected into the typical single mode fibers. And the temperature of the bright spot is reported to be over 10,000 kelvins. And after the fuse propagation, there remains a periodical void train, as shown in this micrograph. The bright spot is regarded as a plasma, and almost no light can propagate through the fiber after fuse. And thus, various properties have been clarified as to glass fiber fuse. However, no reports have been provided yet as to plastic fiber fuse. Therefore, the purpose of this presentation is first to clarify the plastic fiber fuse properties, and then to explore its applications. So let's move on to the fundamental characterization. Plastic optical fibers used in this experiment were composed of perfluorinated acryl-based material, and the core diameter was 50 microns. And it is multi-mode fiber with a graded index profile. The core refractive index was 1.35, and the optical propagation loss at 1.55 microns was 0.25 dB per meter. The cladding diameter was 100 microns, and the outer diameter was 750 microns. Okay, here I'll show you a movie of the POF fuse propagation. And first, silica glass fiber fuse is shown again. The propagation velocity is about 1.2 meter per sec. It's very fast. And next, plastic optical fiber fuse. And this is the POF fuse. The velocity is only about 0.02 meter per sec. It's very slow. And this is the experimental setup. The laser output at 1.55 microns was used. The movie is now being played 10 times faster, but it's still slow. And this is an example of a microscopic image of the fused path. An oscillatory carbonized curve was observed, and it will be explained later in this presentation. And you can watch this movie anytime at YouTube. And next, we investigated the fuse propagation velocity as a function of the power density. The velocity increased linearly with increasing power density. And this shows the comparison with silica glass fiber fuse. And from these results, we know that the minimal propagation velocity of the POF fuse is about 22 millimeter per sec, which is 1 to 2 orders slower than that in silica glass fiber fuse. And also, the threshold power density of the POF fuse is about 6.6 kilowatts per square centimeter, which is about 200 times lower than that in silica glass fiber fuse. So why is the threshold so low? This figure shows the optical absorption plotted as a function of temperature. In a silica SMF, the absorption increased drastically at 1100 degrees Celsius, whereas in a POF, the optical absorption increased drastically at as low as 120 degrees Celsius. And this could be the reason for the low threshold power density. And we also investigated the emission spectra of the POF fuse. The left is the POF fuse emission, the middle is the light bulb emission, and the right is the background or sunlight. And from these spectra, we know that no characteristic peaks are observed in the POF fuse emission spectrum. And this indicates that the POF fuse is not a plasma, but an optical discharge or thermal radiation. In using the Planck's law and Wien's displacement law, the temperature of the bright spot of the POF fuse was calculated to be 3,600 kelvins, which is much lower than 10,000 kelvins in silica glass fiber fuse. Okay, and next I'll show some microscopic images of the POF fuse and discuss the propagation mechanism. The starting point, in this experiment, the fiber fuse was initiated by rubbing the open end of the POF with aluminum powder. Though not so clear in this image, the fuse was triggered at the core center. And then, by gradually reducing the optical power, the fuse was terminated. At the time, the fuse stopped, but remained there for several seconds before disappearance. And therefore, the large surrounding area was melted and bending was observed. And this is the micrograph of the POF after fuse propagation. We can see an oscillatory carbonized black curve, and its oscillation period was about 1,300 microns, and which was in moderate agreement with the theoretical ray period in this GI POF. And this fact indicates that the bright spot propagates only along the optical path of a particular mode with the highest energy, providing the bright spot with the energy directly. And when we injected even higher power into the POF, this kind of spiral oscillation was observed, and it was very beautiful. And we observed a region where the oscillation direction changed from clockwise to counterclockwise, as well as a region with another propagation mode. When the optical power was even higher, sub-watt order, then we sometimes observed a spontaneous burst, and the fuse propagation was automatically stopped. This is a magnified view of the burst, and we can see some gas generated around here. And actually, we found that after the fuse passage, sometimes voids are left periodically along the black curve. The formation of these voids is quite unstable, but somewhat similar to the formation of the void train in glass fiber fuse. And then we developed an easy method for artificially terminating the POF fuse propagation. And this is a metal ring. And by pressure bonding the metal ring, composed of nickel in this case, an abrupt mode conversion is induced, and it enables the termination of the POF fuse propagation. And there are two interesting features of this method. One is that the termination can be achieved without bending. And the other is that after removing the metal ring, the shape of the POF returns to the initial state due to its elastic deformation. And finally, we measured the optical propagation loss of the POF after fuse passage. According to a simple cutback method, the optical loss was calculated to be about 1.4 dB per centimeter, which is too high for telecommunication, but much lower than that of a silicate fiber after fuse. And what's more, the black curve is basically a carbonized one, so it's electrically conductive. And this means that the POF after fuse can propagate light and electric current simultaneously. So this configuration would provide a long photoelectric interaction length, and so some device applications might be possible. Okay, the final topic is the sensing applications of the POF fuse. And to date, glass optical fiber fuse has been used to develop strain, temperature, pressure, and refractive index sensors. The basic idea is that the voids of the fused glass fibers can be treated as an optical cavities and can be used as interferometers. So what about the sensing applications of plastic fiber fuse? Several sensing applications of fused POFs have been already reported, such as strain, temperature, moisture, force, and curvature sensing. However, all of these applications were based on power information, and the stability was not sufficiently high. So we thought of a new magnetic field sensing. Here's the motivation. Optical fiber sensors are not influenced by electromagnetic noise, but the fiber optic magnetic field sensing was difficult. Conventionally, fiber optic magnetic field sensing was performed using high-cost specialty fibers, such as terbium doped fibers and magnetic liquid field hollow core fibers. They're expensive. Therefore, highly sensitive, low-cost fiber optic magnetic field sensors are highly demanded. Then we discovered that the fused POF response reacts to magnetic field. Using this property, we came up with an idea that multimodal interference in fused POFs will lead to highly sensitive low-cost magnetic field sensing. And this is the experimental setup. The fused POF was sandwiched between two silica SMFs, and the broadband light was injected, and the transmitted light spectrum was observed. And these are the experimental results. As you see, the magnetostriction was induced only in a fused POF. In other words, when magnetic field was applied, the length of the fused POF became slightly longer, while the length of the non-fused POF didn't change. Then, these are the multimodal interference spectra of the non-fused and fused POFs. When magnetic field was applied, no peak shift was observed in the non-fused POF, but the peak was clearly shifted in the fused POF. And this result shows that the fused POF can be used for magnetic field sensing. And note that this method is based not on power, but on frequency or wavelength, and so the stability is much higher. The POF length dependence of the sensitivity was also investigated, and the longer POFs led to higher sensitivity. The obtained sensitivity was very high, and with this method, a small magnetic field change of 45 microteslas can be potentially detected, and which is over 100 times smaller than that of the conventional method. And we are now planning to perform material characterization, especially for clarification of the magnetism origin, and optimization for higher sensitivity or stability, investigation of magnetic field direction, demonstration of electric field sensing, and applications to current sensing, and many others. The magnetism analysis is now going on using SQUID and Raman spectroscopy. So, conclusion. We've presented the characterization and applications of plastic optical fiber fuse, including the very slow propagation velocity or very low threshold power density, and many others. So I'd like to finish by thanking you all for your attention. Thank you very much.
Thanks, Professor Isuki, for your excellent talk. And now the floor is open if anybody wants to ask any question to Isuki. If not, then probably any students wants to communicate with us, write to Isuki, and then I think he'll be happy to respond or interact with the students. Thanks. I'll hand it over to the next chairman.
Okay, thank you very much.
I think.
Thank you, Prof. Azizo. I'll take over. Hi. So our next presenter is P. Sustita.
Hi, can you hear me?
Yes, yes.
Can you hear me loud and clear?
Yes, loud and clear. So can you please share your presentation? And before that, I think Prof, we will need Prof. Mizuno to stop sharing his slides so that we can have Sustita to share hers. Okay.
So can you see my slides?
Yes, yes. Can you turn into full screen, please?
Yeah, hold on. Right?
Oh yes. Yes, yes. Oh, sorry. I should have introduced you as Associate Professor Sustita from NQEL, IMEN, UKM. So without further ado, I would like to invite Prof to start your presentation. You have 15 minutes presentation, also followed by 5 minutes Q&A. The floor is, the screen is yours.
Thank you, Dr. Lim. So very good afternoon. A very good afternoon to everyone. So my name is Susie and I'm from IMEN UKM. So the title of today's talk is Kretschmann-based surface plasmon resonance for biosensing at 670 and 785 nanometer wavelengths. So this is the outline of my talk today. So I will just cover some introduction, theory, methodology, and some of the work that we have done on Kretschmann-based SPR sensing, including different types of material and also sensing of different types of analytes. So before that, I'll go into some introduction about chronic kidney disease or CKD. So at the end of 2017, around 3.2 million patients received dialysis, and it is expected the number of patients will reach up to 4.9 million by 2025, right? And CKD can be caused by various factors, including those listed here, right? And in Malaysia, there are more than 40,000 individuals on dialysis with more than 7,000 new patients every year. And the cost of treating CKD has increased dramatically, and in 2016, it is 1.12 billion. So in dialysis methods of CKD patients, they are divided to hemodialysis or peritoneal. And these current dialysis methods are either time-consuming, bulky, or only available in hospitals or dialysis center. So what we are trying to do is having a point-of-care type of dialysis method. And the difference between hemodialysis and peritoneal dialysis is in hemodialysis, the blood is pumped out of your body in an artificial kidney machine. But in peritoneal dialysis, the inside lining of the belly acts as a natural filter. Okay, so this actually lists down the kidney waste in the human body and also the blood sugar levels chart. So IMEN has been recognized by the Ministry of Education as a higher institution of excellence, HICOE, for developing peritoneal dialysis point of equipment to cater for CKD patients in Malaysia. So lab-on-chip-based sensors for CKD, there are conventional methods and also new LOC-based methods. So basically, we are moving away from an invasive method to a non-invasive, such as detecting CKD either in saliva, blood, or urine or sweat, right? Not blood. And this Kretschmann-based surface plasmon resonance or KSPR, it can be a good choice for early detection for fundamental studies of SPR detection of bio-nanomolecules. So some of the common bio-nanomolecules used in CKD is such as urea, uric acid, creatinine, and also glucose. So these are being detected at IMEN UKM. And in terms of the materials that are being used, we started off with the basic 50 nanometer gold layer, followed by a hybrid layer, zinc oxide, gold, and also silver. And we moved on to other types of hybrid layers such as GO, TiO2, and also more recently on MOS2 and graphene, which are 2D materials. Okay, so now I'll touch a bit about optical biosensors, although I think all the plenary and keynote speakers have already done a lot of introduction, so maybe I'll just skip through very fast. So as we all know, the working principle of optical sensors, so basically we can utilize the intensity or amplitude based sensors, or we can utilize the frequency or the wavelength, which is what fiber optic sensors are based on. And in this word, Crashman SPR is mostly on the phase or the angular modulating sensing. And of course, last but not least is the polarization modulating sensing. So these are some optical biosensor applications. So my work is concentrated on health and medical applications. And different parts of a biosensor, basically you need to have a sample, biological and elements, either enzymes, antibodies, or aptamers, a transducing method. In this work, we are using optical and also electrochemical, and finally the signal processing. So as mentioned, this work combines both the optical detection method and also the electrochemical method. So SPR, I think Prof. Aziz has already touched on this earlier on, so I'll just go through very quickly. Basically, it is an interaction between the incident optical wave together with the electron gas which exists in the metal thin film, right? So when the wave vector length is equivalent between this incident light and the SPP wave vector length, we have a resonant condition which occurs above the thin metal layer. And for SPP to be ignited, we need to use the P polarized light, and it does not occur in the S polarized light. Okay, so this just shows the prism setup together with the laser and also the detector. And this is the sensor slide, which comprises of chromium, gold, and also various types of materials that we have evaluated. And it is combined with a microfluidic channel where analytes can be flowed through. And this shows the SPR curve where when a resonance occurs, there is a dip in the reflectance collected by the detector. And with the presence of different analytes, which changes the topmost refractive index, there is a shift in this SPR curve. And we detect the change in this angle shift, right? Else than optical sensing method, we can also combine including dual sensing mechanism. So as we all know, electrochemical biosensing involves 3 electrodes. So we have a counter electrode, reference electrode, and also a working electrode. And the way it works is there is a reduction and also an oxidation of chemicals. And the change in the current when these 2 reactions take place is used as a sensing mechanism. And there are various types of electrochemical methods that can be used, including CV, EIS, DPV, and also SWV. So we are using the CV method, which is cyclic voltammetry. Okay. And in our lab, we have the equipment which combines both SPR, optical method, and also electrochemical sensing method. So there can be a cyclic voltammogram and also an SPR refractive curve. All right. Some of the previous motivation that allowed us to work on this, such as the diagnosis and the detection of SARS-CoV-19 virus. This was way back in 2020. So basically, it combines the usage of plasmonic sensing on gold nano islands with the presence of a thermal effect, right? And it can detect as small as 1 picomolar, right? Also, point of care applications for these SPR devices, which combines the usage of LED illumination and also CMOS circuitry on a plasmonic chip. So this is for the detection of proteins with and without the binding effect, right? It shows a change in the intensity of the light. Also in this method, it uses single chip SPR and also fluorescence ELISA assay. This is for the detection of PSA, prostate specific antigen, PSA. And there is a shift, an increase in the shift when there's an increase in the PSA molarity. So this shows different types of LOC application. So else than sensing, these plasmonic effects can also be used on various optoelectronic devices, such as in photodetectors, in this work, this plasmonic effect, where we have a gold layer, and it's used in a high-speed photodetector with germanium core over here, and gold lateral cladding on a silicon optical waveguide, right? So I think this has been touched a lot by Prof. Aziz earlier on. Similarly, for lasers and also laser array, and in this work, the plasmonic effect is used using a nanometallic structure with zinc oxide nanowires, and it lasers at 372 nanometers. Okay, and we move on to solar cells. So there are 5 substrates over here. A control substrate. S1 contains only gold and titanium dioxide nanoparticles. S2 contains both the titanium dioxide nanoparticles and suspended gold titanium dioxide core shells. And S3 combines, they are both suspended and also within the gold, the titanium dioxide nanoparticles. And last but not least, we have P25 nanoparticles. So as can be seen here, the presence of these gold titanium dioxide core shell nanoparticles plasmonic effect increases the performance of the efficiency up to 18.24%. So in this work, basically we combine the FDTD numerical method using numerical, and also we have done our experimental work using this BioNavis equipment available in IMAN UKM. So else than detecting layer properties such as refractive index, thickness, and so forth, the equipment is also capable on detecting molecular interactions such as kinetics, affinity, concentration, and so forth. Okay. And some of the common figure of merit that is used in surface plasmon resonance is such as the sensitivity, which is the amount of shifting of the angle divided by the refractive index. Also the minimum reflectivity given by this value over here, the full width at half maximum, which is the breadth of the SPR curve. Right, we begin with some results from the detection of urea and creatinine using metal thin films. This is with graphene. So these are some of our work which has been published. And basically we detected at 670 and also at 785 nanometers visible wavelength. And it can be seen here, we have detected both for urea with the presence of urease and also creatinine with the presence of creatinase enzyme, right? And as can be seen here, for 50 millimolar of urea, the sensitivity is highest at 16.2 degrees per molar, right? So for low molarities, the sensitivity is high. And as you go up to higher molarities, there is saturation which occurs and the sensitivity decreases. Okay. So similarly for for creatinine and creatinase, again, at low molarities with the presence of the enzyme creatinase, we get a high sensitivity of 10 degrees per molar. All right. The equipment is also capable of detecting the refractive index of each molarity of the solutions. And these are the list of refractive index that was obtained. Okay. So next we move on for the detection of glucose. So just now it was urea and creatinine with the presence of urease and creatinase. Detection of glucose was also done with the equipment, and we compared the results with the FDTD simulations. And it shows for glucose concentration from 1% right until 5%. And there is a close similarity between the FDTD and also the experimental work. So the upper one here is for 670 nanometer wavelength, and the bottom one here is for the 785 nanometer wavelength. And it also gives us the sensogram. So this is basically the angle shift versus time, right? So it's called a sensogram for both 670 and also 785. So as the molarity increases, there is an increase in the shift versus time. Okay. So next we evaluate different types of material, and in this first work here, we looked at the effect of chromium and also various types of metals, gold, silver, and also copper. And basically the 50 nanometer gold gives the best reflectivity and sensitivity. And the presence of chromium is actually quite negligible in this work. It shows in this work. And next, we added an ITO layer of 10 nanometers. and it shows there is a shift, but still the reflectivity is still acceptable at 0.25. So this work is on further using an optimization method to optimize the thickness of the various layers in order to get the best result. So this is the comparison of SPR detection in water and also in glucose. So it's a FDTD simulation. Okay. We also look at hybrid layers of silver, gold, and also zinc oxide. And again, we use optimization methods, Taguchi optimization method, to find which performance is the best for all the different layers, right? So moving on. And in this work, we looked at the effect of copper, GO, and also titanium dioxide for 3 different wavelengths, which is 633, 670, and also 785. And we have an improved sensitivity of 13.20% at all the 3 wavelengths, comparing with a purely silver layer, right? So hybrid layers, depending on the thickness and also the refractive index of the material used, can enhance the sensitivity of the SPR sensor. Next, we move on to the usage of 2D materials for the sensing of glucose, urea, creatinine, and also uric acid. So this is actually comparing 3 different structures. We have the AU structure, just a simple gold layer. And then we added on the MOS2, which is a 2D material. And finally, the MOS2 was, another layer of graphene was put onto the MOS2 layer, which is shown by this graph over here. And we can see here, this is for 670, and also this is for 785. And the AU MOS2 graphene gave the best sensitivity of 230 and 172.86 respectively. And this shows the reflectance curve for both structure 1 and also structure 2. And we can conclude that structure 2 gave the best sensitivity of 202.02, right? So which is increased compared to 670 nanometers. Next, some simulation work on sensing of uric acid. So we used the similar structure, AU, MOS2, and graphene, both at 670 and 785. And we obtained that at 670, it is 14.6% higher compared to 785, right? And we also, prior to sensing uric acid and so forth, we just needed to see the working mechanism, and we looked at ethanol sensor of the fabricated material. This shows the AFM image. So this shows the thickness of the graphene, followed by the Raman spectra, which shows that a graphene has been deposited on the AU-coated SPR sensor. And it also shows the respective peaks in the Raman spectra for the MOS2 layers. So this shows the angular sensitivity of both the AU graphene, which is 7 layers of graphene, and MOS2 of 3 layers. So with the increase in the ethanol concentration, the angular sensitivity increases as well. So the sensor is capable of detecting ethanol. This is just a proof of concept. So we also look at combination of SPR with electrochemical sensing. So this work is still ongoing, right? And we are just growing the material sense, just starting our sensing mechanism, both the EC and SPR. So it's work in progress. And other optical sensors that we develop in our lab is biosensor optical circuit. This is a circuit which is a lab on chip. So you have a light laser and also a detector, and in between you have a waveguide based sensor, SPR sensor. And it was used to detect glucose in urine samples. So these are the transmission and reflection results. And some other lasers and photodetectors which use plasmonic effects in our lab, right? And this actually is a fiber optic sensor that we developed using aluminum doped zinc oxide. So basically it was used to develop a UV sensor where in the presence of zinc oxide with 1% of aluminium and stannum, we can see here in the presence of UV light, the zinc oxide nanorod showed an up and down trend versus the zinc oxide nanoparticle, right? So this is a UV detector that we developed in our labs. Also, the plasmonic effect can be used on microring resonators as an element to, for sensing purposes and even for optical communication. Right? Go on fast because of time. So in summary, the Kretschmann-based SPR sensing, it can be used for point of care and also lab-on-chip applications, as well as for plasmonic lasers, photodetector, and also microring resonators. So at IMEN, I've just showed a few examples of different materials and different analytes that we have sensed using both numerical FDTD and also the BioNavis SPR equipment. So in future, these fundamental studies can be deployed into fiber optic based sensing or LOC for portability. So I'd like to thank my students, also the funders, and our collaborators all over the world. Thank you very much.
Thank you, Prof. Susi, for the interesting presentation. So the floor is now open for Q&A. So we would like to invite some questions from the floor. Anyone?
Thank you very much for your nice presentation. Actually, I would like to ask your electrochemical sensing. You have pointed out. So for the modification, you have used graphene oxide or graphene?
For the electrochemical sensing?
Yes, you have modified your surface. I have seen that either graphene oxide or graphene.
We use a multi-wall carbon nanotube together with polypyro.
And also you somewhere maybe used graphene oxide, maybe?
All right, that was here. Yeah.
Yes?
Yeah.
Yes.
This is for SPR, not for electrochemical. This is for SPR.
Oh, SPR. Okay. Okay, thank you. Actually, I was a little confused. Okay, thank you.
Okay.
Actually, graphene oxide is not so electrochemically. Actually, the surface is not so stable, and that is why I'm asking this question.
Yeah, we use for electrochemical sensing. We use multi-wall carbon nanotube together with polypyro.
Okay, thank you very much.
Thank you. Any other questions before I ask mine? Okay, Prof. Susi, if you don't mind, I have some silly questions. I've seen one of your work is related to urea detections. Just wondering, did you use any bioreceptor or any form of receptor for this kind of protein detections? Yeah, for example, urea or uric acid.
Yeah, we deposit the urease enzyme on the sensor slide.
Okay, so are those enzymes commercially available, or is a product that is developed by your group or other groups?
As of now, we use the commercially available ones, but we do some plasma modification on it, so that this is to optimize the layers, to increase the capturing of the analyte and the ligand layer. So we need to do some functionalization, including plasma processing of the layers.
Thank you. Just now there was you presented a work on SPR using waveguide. So yeah, there was some graphs, but may I know how big is the waveguide? Did you make the waveguide or is a simulation? Sorry, I didn't pay enough attention to it, so I just wonder if you can elaborate more about this work.
On the waveguide, is it on the
yes.
microring?
Yeah, probably it's microring, or did you use any grading-based SPR device?
Grading-based, no. So far, I don't work on grading-based SPR device, no.
Any reason why? So I just want to ask for your opinion. Any reason why KSPR system is actually more welcoming, or maybe more popular among all the configurations in the market now? Any reason why?
Is popular. Okay, so because it's using a phase change, right? And we know phase change is very sensitive to refractive index changes. right? But having said that, you know, for initial fundamental studies, yes, it is preferable because you can find the optimum layers needed to functionalize for biosensing. But moving forward for portability and so forth, so the KSPR is a equipment. So it is mainly for fundamental studies, but and the reason why it's very interesting is because it's sensitive. It detects the phase of light, right? And you have a single wavelength of light versus wavelength interrogation uses a monochromatic light. So you have multiple wavelengths. So your power is actually distributed among all the wavelengths. And so for fundamental studies, you know, initial biosensor development, this KSPR method is very valuable in my opinion.
Thank you very much. Probably, if you don't mind, we can talk more about this later. I'm working on TFPG.
Yeah, sure.
I'm working on TFPG. So SPR TFPG. So
all right. Sure,
yeah.
Dr. Lim, no problem. I'll be happy to work with you.
Okay, thank you very much. So,
thank you, Dr. Lim.
Yeah, we will now take a break. Yeah, we were a bit slightly over time, so we only have. I hope everyone doesn't mind. Don't mind that we will take a 10 minutes break, and we'll come back at 3:45. And the next performer, presenter is Dr. Muhammad Al Mamun. Yeah. Thank you.
Actually, I'm the next presenter. Hello, anybody here?
Yes, yes. We will take.
I'm the next presenter, so I'm trying to share my screen actually.
Yes, we can see your screen. Can you turn into full screen, please?
Okay, I will wait. But is it okay now? I actually for verification. My screen is sharing.
Yeah, you are sharing your PowerPoint.
Yes,
but
yes.
But it's not a full screen yet.
Okay, okay. Is it okay now? Actually, when I will start, actually, if there is no problem.
Please. You can turn it to full screen and keep it on the first page. Mr. Muhammad Awad Makmum to present his topic on scrap gold recovery, recycling, fabrications, and electrochemical characterization of low-cost gold electrode. So, yes, Muhammad, can you please, yes, thank you. Yeah, the floor is yours. Thank you.
Assalamu alaikum. Good afternoon. Thank you very much for giving me a platform to present my work in such a prestigious conference. In this conference, actually, I am going to present a tiny part of my PhD research. My PhD research actually focused on the low-cost electrode-based electrochemical DNA biosensor for the cancer biomarker detection. Actually, it's a small part. In this part, actually, I try to fabricate a low-cost gold electrode that will be used in my future work. It was from scrap gold. So this is the outline of my presentation. First, I will introduce about gold and the problem, objectives, and we'll discuss the experimental part. And finally, I will discuss results and discussion and conclusion. So, gold. Scientists believe that gold arrived on Earth after the collision of two neutron stars in space about 3.9 billion years ago. Then, 40,000 years ago, first gold flakes were found in a cave. And gold has been used frequently. Gold used in different civilizations, especially from the ancient Egypt. As you will know that for the preparation of their coffin, they also used gold, 3 layers of gold. Even the modern chemistry and modern medical science, which has been introduced by the alchemy, their central research exploration, central dream was to prepare gold from other metal. Because actually gold has some unique properties. It is resist most acids, especially it is dissolved in aqua and reflected heat and light. It is also biocompatible. And due to reflect heat and light, it is also used in space also, you know, because it can protect sunlight in the spaceship. So there are a lot of use of gold due to its excellent characteristics, properties. So it is not only used in the currency in government, but also it has been used to different analytical purpose also. For example, it is a very good heterogeneous catalyst, and for sensor development, it is frequently used. And in biosensor technology, as you know, that it is also used as substrate. Even the gold nanoparticles, different shapes and size has been used in different technologies, especially the biosensor technology. For example, COVID kit test, you know. So cancer detection, cancer therapy, photothermal therapy, and also it is frequently used in different electronics, you know, the CD and mobile phone technology. So its use is tremendously increasing day by day. But one important thing is that the price is not actually decreasing. The price is the most important challenge for gold using in different sectors. But another important thing is that the mining gold, what is the source of gold? Actually, from the alchemy age, the peoples are trying to make gold from others' metal. But in laboratory, it is possible, theoretically, to make gold from other metal, for example, from lead. But it needs extremely high amount of energy. The cost of that energy is tremendous. For that region, it will not be feasible, economically viable for the preparation of gold from other metals. And that is why the alternative way, still now it is continuing, that gold is mainly extracted from the mine you see from this chart that more than 74% gold has been extracted from the mine, and almost about 26% gold is recycled from others. So scientists actually believe that after 20 years, if there is no new mine actually discovered, after 20 years, all the mine gold will be exhausted from the mine. So what will be then actually? So what is the alternative way? And that is why actually the gold price will increase day by day. So how we can meet our future demand, future supply? So from that respects, actually researchers, scientists, they are thinking that what the most alternative way is to recycling of gold, and gold-based products should be used repeatedly. How could we use the same gold products after recycling and then repeatedly use? So it is the focusing point, should be the focusing point of the research. And from that point, I have just a teeny step. I try to actually recycle gold from jewelry things, damaging things. And after recycling that gold, I have prepared my electrode, and that electrode has been used for the electrochemical performance. Either it is working properly or not. So this is the these are the methods actually which are used for recycling of gold from different sources. So among them, most popular method is aquaresia process, because it is able to produce highly pure gold. Actually, for the electrode preparation, as you know that the electrode surface is very sensitive, you need a very highly pure gold. Minimum 99.9% pure gold is required for the electrode preparation, and that is why from that purpose, aquaresia process is a very simplest and fastest and most robust them and efficient method, and we have followed this method for the recycling of gold. We reviewed some literature, and we have found very few literature in this field that they have recycled gold and then used for the electrode preparation. In 1997, some scientists have gold microelectrode arrays has been fabricated and has been evaluated electrochemical performance. Their electrode surface was uniform, but not satisfactory in terms of repeated use. Actually, their electrodes were actually the single-use electrode. And then in 2000, we have found some researchers tried to build CD drawers actually using recordable CDs. They have manufactured, they have fabricated electrode arrays, and those electrodes are also used for single-use electrode, not for multiple use. And then in recently 2018, as Santos and his workers, gold leaf sheet based electrodes they have produced from wedding candies and decorative crafts, and they are disposable, wearable, but the reproducibility was not actually sufficient. So we have found that what is the problem actually? Recycle gold used for the electrode preparation. We have found that from the reported literature that the lack of sufficient reproducibility, multiple use, and renewability of the electrode surface. Because reproducibility, renewability, this is very much emergency for the electrode biosensing technology. If you want to repeatedly use the same electrode for several times. And another is the price of gold. It is another issue, and highly pure gold. So that keeping those things in mind, we have actually set our goal, objective, to recycle the pure gold from jewelry scrap gold to fabricate the gold electrode using that recycled gold. And we have checked the electrochemical performance using cyclic voltammetry, differential pulse voltammetry, and electrochemical impedance spectroscopy. And electrocatalytic behavior we have checked after modification using gold nanoparticles, and the reproducibility and renewability of the recycled gold electrode have been also checked and reported later. And this is the well-established method, that is the flow sheet for the recycling of gold from the scrap gold after washing, and then the aquaresia, dissolving in aquaresia, and then after vacuum filtration, the solid sludge has been separated from the solution, and the gold solution has been precipitated by using sodium metabisulfate. In this way, it is very well-known procedure and very simple procedure by which we have recycled that gold. And that gold, recycled gold, has been used for the fabrication of my electrode. And to save the electrode materials, we have used the conducting materials as copper rod, and that copper rod has been joined with my recycled gold tablet, and that joint electrode has been inserted into a Teflon tube. And after that, after polishing and smoothing the surface, the final gold electrode has been used for the electrochemical characterization. And also the catalytic activity, to check the catalytic activity, we have electrocatalytic activity. Actually, we have modified that recycled gold electrode with gold 10 nanometer gold nanoparticle. This is a very simple method. By drop casting method, we have actually fabricated this modified gold electrode, and then that's the performance of that fabricated electrode has been checked by electrochemical workstation. Actually, already my previous speaker, already the principle has been explained. Just I'm discussing in brief that the most important part of the electrochemistry system is the 3 electrode electrochemical cell, which include 3 electrode. One is auxiliary electrode, that is called counter electrode, and reference electrode, and the main electrode, what is called the working electrode. This electrode is actually my recycled gold electrode. So after attaching with the potentiostat, we have measured using different techniques. Cycling voltammetry, this is the result of differential pulse voltammogram, and this is electrochemical impedance spectroscopy result. We have taken potassium ferrocyanide solution as a redox species, and we have found very good response and in all the techniques as typical electrochemical behaviors we have found, and also for the well-defined redox peak we have found around Atherbold and Atherbold. So from the preliminary test, our recycled gold electrode is quite good for the future application. And also the validity, another important electrochemical parameter, that is Rendell's septic equation, by which we also apply for this electrode. Either the equation is valid for the electrode or not. We have at different scan rate, we have taken this voltammogram, and after getting the peak current, we have found this Rendell's septic plot, and this is a very good linear response we have found. And then we have calculated some electrochemical parameters, and from these parameters we have found that peak current ratio is giving the quasi-reversible charge transfer process on that recycled gold electrode. And others parameter also shows typical voltammetric behavior. And the electrocatalytic activity of the modified electrode have been also tested by the two techniques, cyclic voltammetry and differential pulse voltammetry. We have found very good electrocatalytic activity after modification of that recycled gold electrode. And the modified electrode also satisfy the Rendell's septic equation. And we have also calculated for the modified surface the electrochemical parameters, and charge transfer rate constant we have calculated for both the electrode before modification and after modification, either it is electrocatalytically active or not. We have found from the charge transfer resistance, we have found that the modified electrode is giving more charge transfer rate constant than the unmodified electrode. So from this calculated result, we can conclude that the modified electrode is showing the electrocatalytic activity. And also after modification, the over potential has been also decreased compared to the bare electrode. And also the reproducibility of the same electrode has also been checked. We have found about 0.01 to 1.9% RSD, and this results also very good for the use of the electrode for electrochemical purpose. And we also the same electrode, because as you will know that the gold electrode is very expensive, so the same electrode should be used in different repeated use. It is very important, because if one electrochemical device or any test kit, if you are not able to repeatedly use, one time use, if you it is gold substrate, it is very expensive. So if you can use the same sensor or same device or same kit several times, it will be more cost effective, and that is why so the electrode is either renewable or reusable. This modified electrode has been actually after polishing and different stage, and the same electrode has been verified by cyclic voltammeter, taking cyclic voltammeter. We have found that the after removal the surface, it is behaving the previous original electrode little. Actually, the range was 98 to 1 to 99.9%. So it is quite acceptable, because you know our acceptable limit is not less than 98%. So from that point of view, the recycled gold electrode is very good for the repeated use also. So this is the conclusion. Actually, we also calculated the cost factor. Comparing with the commercial electrode, we have found that about 20 times lower. Our recycled electrode will be the 20 times lower cost than the commercial electrode, and it will be, of course, will encourage the especially the electrochemists who are working with working electrode, but it is very expensive. So for the least developed countries, electrochemists, they can build actually low cost electrode by this process. It will introduce a platform for this. So I'm thanking to my University of Malaya, and also the government of People's Republic Bangladesh for providing the financial support for this work. And thank you very much. If you have any question, I would be very grateful to you.
Yeah, thank you, Muhammad. Yeah, interesting presentation. Yeah, the floor is open for Q&A. Yeah, feel free to ask if you have any questions. Yeah. Anybody? Okay. That there's no question. So yeah, thank you, Muhammad, once again. Yeah. So I will thank you very much. I will hand over the sessions to Dr. Chong Wee.
Thank you, Dr. Lim. Can I invite the next presenter, Mr. Umar Mustaqim, to share your slide?
Okay, Doctor. We're presenting my slide.
Can I also ask Muhammad Al Mamun to unshare your slide, please? Thank you. All right, okay. So a very good evening to everyone. We'll continue the session with presentation by Mr. Umar. With the title of his presentation, High Power Multi-Wavelength Double Clad Erbium Ytterbium Photo Fiber Laser using 2 and 4 mode fiber filters. Okay, presentation is 20 minutes, 15 minutes of presentation plus 5 minutes Q&A. Okay, I'll pass the screen to Mr. Umar. You can start when you're ready.
Assalamualaikum and very good afternoon to all of the listeners. Thank you for Dr. Chong for the introduction. So my name is Muhammad Umar Mustaqim bin Isnahini from Photonics Research Centre. I'll be presenting my current work for the high power multi-wavelength double clad erbium ytterbium coated fiber laser by using a 2 and 4 mode fiber filter. So this is the overall content that I'll be presenting, and I will present a little bit introduction of my research and the objective and the whole methodology of my research, and follow up with my result and the conclusion of my research. So first of all, I will introduce you about the multi-wavelength fiber laser. So fiber laser, generally it will generate more than, basic laser will generate actually one wavelength. So multi-wavelength, as the name proposed, it will generate more than one wavelength of laser. So, as shown as a figure from this slide, there are multiple lasing lines generated from the setup, which is from the picture, which is 4 wavelength. So the use of multi-wavelength fiber laser is generally for many various applications, including instrumentation, testing, optical communication, and optical sensing. And there are multiple methods in generate multi-wavelength fiber laser. And some of it is by using Mach-Zehnder interferometer, using single mode, multi-mode, and single mode structure, and even by using SegNet loop. So the idea of ComFilter to generate a multi-wavelength fiber laser, the main component is the filter, which work as same as the Mach-Zehnder interferometer, and the theory already just presented in this morning. So I just give you the brief introduction about what is Mach-Zehnder interferometer. So the idea is Mach-Zehnder interferometer is to generate an interference at the output of the whole design. So as you know, the input light, it will be at the same phase, and there will be, and this Y splitter over here will work as to generate a different delay, different phase. Will generate phase delay by having 2 different length of splitter at the upper arm and lower arm, and then it will be coupled back again, and due to the different length of propagation, it will generate an interference that and we will generate interference at the output fiber. So the next introduction is about the high power fiber laser. As usual, most general laser, they generate around milliwatt output power. So high output power is generated by different type of structure, which is known as the cladding pumping setup. So as we know, to generate a 2 micron fiber laser or 1.5 at different wavelength, we need a different earth rare doped fiber. So as example, thulium is generated to generate 2 micron at a 2 micron wavelength. So for this setup, erbium ytterbium, using erbium ytterbium doped fiber at the core of the setup, and to generate 1.5 wavelength fiber laser. So the whole setup is cladding pumping. They actually have two cladding, which is the core will have the rare earth dope inside the core, and the light will propagate inside the first cladding, and the second cladding is used to trap the light inside the first cladding, so it will generate more high output power at the output of the fiber laser. So in order, what they use to generate multi-wavelength high output power, high output fiber laser is the objective is to generate a high output multi-wavelength fiber laser, which also have a good stability, and we propose to have a very compact setup for future application in industry. So in order to generate multi-wavelength fiber laser, the main component is to develop our comb filter, which in this case I'm using a single mode, multi-mode, and single mode structure. And the single mode, this is the whole setup that we use. Actually, we custom splice the splicing point at both of the end, so it will introduce phase difference. So at the end of this fiber, it will generate an interference. So this image shows the image for 2-mode fiber, and the same setup is has been used for the 4-mode fiber. Both of the fiber are constantly at a length of 5 meters, and it is pulled in 5 centimeter radius. So the most important part in generate what we call it multi-wavelength fiber laser, the FSR is one of the most important part in generate a multi-wavelength fiber laser, because by have different FSR, it will have a different application. So for my study, I'm using one pair of 915 LD continue with a pump combiner, and 4 meter EYDF. It will absorb 91.5 nanometer laser and will generate output wavelength at 1.5 nanometer, and it will go to 70-30 coupler. 30% will go into feedback, into the feedback of the cavity, and the 70% will go out of the as an output of the fiber. And after the coupler, it will splice again, splice into an isolator, which followed with a comb filter, which in this case will be 2-mode fiber or 4-mode fiber. Then continue with polarization controller and high nonlinear fiber. The use for high nonlinear fiber is to generate a more stable output of multi-wavelength fiber laser. The problem in generate multi-wavelength fiber laser is because of the mode computation. By introducing high nonlinear fiber, it will reduce the mode computation and will generate. It will induce 4-wave mixing inside the fiber and will generate better stable output fiber laser, multi-wavelength fiber laser. So follow with my result. This is based on my result. We are using 2 fiber. So there are 2 fiber over here. The blue one is for the 2-mode fiber, and the red one is for 4-mode fiber. The extension ratio for the 2-mode fiber is 3.6 dB, and for the 4-mode fiber, it has 7.7 dB extension ratio. The FSR for the 4-mode is 0.95, while for the 2-mode fiber is 0.56 nanometer. So after we splice the comb filter into the whole cavity, it generate this 20 for 2-mode fiber. It generate 22 lasing lines in 30 dB SNR higher from the noise, and while for the 4-mode fiber, it generates 7 lasing line. Both of the results show that the FSR for the value of the whole cavity is the same as the characterized value for the comb filter. The output is recorded at 9 watt pump power. And then we follow up with to study the effect of HNLF. We record the same result at the same pump power without using HNLF. As you can see, that for both result, we can see that the lasing line is reduced. as before they have 22 lasing line, then it reduced to 7, and just now is 7 lasing line, it will reduce until 4 lasing lines. So, and the output is quite unstable. So based from the from our experiment, the HMNF really helped to generate better multi-wavelength fiber laser. So this is the output spectrum for the at the different pump power. As we can see, by increasing the pump power, the lasing line above the noise is higher at the output power, and we set it to 9 watt because it is the limit we can increase for our whole setup. From the output, we recorded the 2-mode fiber to generate around 553 milliwatt with the efficiency of 6.4%, and a 4-mode, while using 4-mode fiber, it will generate around 443 milliwatt with the slope efficiency of 5.3%. And this is the result for the stability for the 2-mode fiber. It has power fluctuation of 2.61 dB, while the wavelength drift is around 0.56 nanometer. And this is the 4-mode fiber. The stability, we can conclude the stability, the output is very stable, which has a power fluctuation of 2.85 dB, and a wavelength drift is around 0.2 nanometers. And this is a table show the comparison between different literature by the lasing line and the maximum output power, and also with the efficiency. As you can see, our maximum output power is much higher compared to others, follow up with our maximum line, and the efficiency proposed from our work is much higher compared to other literatures. So as a conclusion from the study, we can generate 22 stable multi-wavelength lasing line using 2-mode fiber, while 7 lasing lines, only 7 lasing lines for 4-mode fiber. And the optical power generated by the proposal setup generate relatively, higher output power with more lasing line compared to previous literature. So that's all for me. Thank you.
Thank you, Mr. Omar, for your presentation. We open the Q&A to the floor. Any question from the floor? No question? Right, in that case, thank you very much, Mr. Omar. We'll invite the last presenter of the day, which is Mr. Azil Kenza. Can you share your slide? Thank you, Mr. Omar. Is Mr. Azil Kenza? Oh, okay. Okay, our last presenter is Mr. Azil Kenza. Yes, he's from, sorry, Dr. Azil Kenza, sorry. Pardon me. So the title of her presentation is D-shape optical fiber sensor for heavy metals monitoring. She's from Farhat Abbas Satif 1 University from Algeria.
Yes, I'm from Algeria.
All right, okay. I'll pass the screen to Dr. Azil. If you can put your presentation on full screen, that would be great.
Can you see now?
We still see, I'm still seeing the edit mode. Yeah, can you just press it? It's still on full screen. Can anyone else verify whether you are seeing the same screen as me?
And now?
Still there, the screen. Can you try to just, press the slideshow?
Okay.
Yeah, all right, there you go. All right, Dr. Aziz, you can start whenever you're ready.
Okay. Firstly, I would like to thank everyone in the member committee of accepting my presentation, entitled by D-shaped optical fiber sensor for heavy metals monitoring, especially for water pollution. First, I would like to present myself, Dr. Adil Kenza, from Applied Optics Laboratory, Institute of Optics and Precision Mechanics, Farhat Abbas, City of One University from Algeria. So, we will present this outlines. We will start by water pollution issue and the methods of control. Then we will precise our work on or focus our work on optical fiber sensor. We will explain the theoretical part and experimental part. Especially, we have focused on the D-shaped fibers. We will present our experimental setup, and then we will discuss our results, and then we will conclude by a conclusion. So, water pollution, as we know, is a big problem in our daily life. The center of life that allows us to survive is water, and the most vivacious that keeps us drinking as well. Drinking clean water and pure water is essential for all of us. While consuming it's harder to consume it because of finding multiple pollutants like this one, which is presented in the screen, like pathogen, thermal pollution, nutrients, suspended solids, and radioactive pollutants. So for that reason, we need optical methods, which is categorized as direct and indirect methods. Direct one, which is categorized as atomic spectroscopy, UV visible methods, and infrared spectroscopy. The indirect one is categorized as interferometry, surface plasma resonance grating, evanescent wave spectroscopy, and others. So in direct methods, we have like this atomic spectroscopy, we have UV visible, we have infrared spectroscopy. The indirect one, we have interferometry methods, we have surface plasma resonance, and we have Bragg grating fibers by using this kind of fibers. And the last one is evanescent wave spectroscopy, which will focus on these methods. So our motivation in this part is the D-shaped optical fiber sensor for controlling cobalt chloride. So how we can get our experiment? We will focus, or we will start by identify the pollutant, which is the cobalt. It can be seen that this cobalt is absorbed in the visible range. This spectrum include or present the absorption spectrum of cobalt chloride of solution with the 25 milligram per liter. The spectrophotometer that we have used that exists in our laboratory. The second step is identify the excited source, which is the LED. So it can emit from 400 till 800 nanometers. So this emission spectrum response of the used lens, the LED, can give us a good response of our fabricated sensor. And third step is the process of D-shaped fiber fabrication. The photo or the figure A presents the schematic illustration of this polishing process by making the fiber by making the fiber in contact with the polishing paper. And this C figure, this is the real figure of our D-shaped optical fiber. So after that, we need to characterize our fiber by using optical microscope and the profilometer. So these two figures present microscopic insight of uniform fiber and microscopic insight of D-shaped fiber. So it can be seen that there is a big difference. So our polishing process is effective, and we can use it for making D-shaped fiber, as it can be seen here in the second figure. Second characterization is using this instrument, profilometer, that can give us the roughness and the profile of fiber. So it can be seen here from these two figures that the uniform optical fiber, it has a regular or smooth profile, while the D-shape, it has a D or a D-shape form that can be seen here or here in this figure. Our experimental setup consists using a light source that emits from 400 till 800 with a microscope objective with characterization of 40 with a numerical aperture 0.65. The light here is focused with this microscope objective. It can be guided within this fiber optic with 20 centimeter as a length, and the sensor region here of D-shape is 2 centimeter. The light output intensity, it can be detected by the spectrophotometer that can detect from 300 till 100 nanometer, and the laptop that can plot our final results. So our results, we have the output intensity according to the concentration from 400 till 500 milligram per liter. For 520 nanometer, we have chosen this wavelength because it's the higher absorption of our pollutant, which is cobalt chloride. So the first figure, it can be seen that the output intensity of uniform fiber is greater than the D-shaped fiber. The second one is the absorbance according to the refractive index. It can be seen also, or we can also explain that explain this result by the D-shape. It has a high interaction of invalescent power with the surrounding medium, which is cobalt chloride with mixed with the distilled water. So by using the D-shaped form, we can get good absorbance and a useful tool for controlling or monitoring our pollutants. So like every work, we have some outcomes. We have, firstly, we have started the experience by choosing a pollutant of water, which is cobalt chloride. As we know that this cobalt chloride, it's very dangerous on human health. We can't exceed, if we exceed 0.2 gram per kilogram of weight, it will be very dangerous on the newborn and environment. We have also measured the intensities of transmitted light passing through the solution of distilled water mixing by cobalt chloride in a toxicity range from 100 till 500 milligram per liter for the two forms of fibers, uniform fiber and D-shaped fiber, for length equal to 20 centimeter, and for sensing region equal to 2 centimeter. We have characterized two fibers with optical microscope and make the full characterization of both of them. we have noticed that the diameter of the shaped fiber is smaller than the diameter of uniform fiber because of the polishing process, as we mentioned before. After that, we have found that the absorbance of the shaped fiber is greater than the absorbance of uniform because the light from the environment is interacting directly and more with the surrounding media. So using this technique or enhancing this technique of uniform by using the D-shape, it can be or give us useful and the practical tool for sensing or monitoring water pollution. Thank you for your attention.
Thank you very much, Dr. Zulkanza. Now I open the Q&A to the floor. Any question? Right, if there's no question, I think we will end today's session. So that concludes today's conference. There will be the conference will continue tomorrow at 10 a.m. in the morning with the keynote address by Associate Professor Cheng Yu Hong using the same MS Team link. All right. With this, I thank everyone for your attendance. Thank you for the presenter, Mr. Umar, as well as Dr. Zulkanza. And we'll see you guys tomorrow.
Thank you all. Thank you for you all.
Thank you, everyone.
Thanks, everybody.
Thank you.